Hello, and welcome to Night Cosmos Sleep. Thank you for spending your time here as we step away from the familiar noise of everyday life and look toward the universe in a slower way. Tonight, we will talk about planets that are very far from Earth. They do not orbit our Sunday. Instead, they orbit other stars. Scientists call them exoplanets, or planets outside our solar system. What makes this especially interesting is that some of these planets may have water. It could be water in the atmosphere. It could be ice. It could even be very deep oceans, hidden beneath a thick layer of gas or under a cold shell of ice. But for now, we still cannot say for certain that we have truly seen an ocean on a planet that far away. So how do human beings know anything about this? Scientists cannot fly to those planets. They also cannot clearly see the surface of an ocean there, the way we can see the oceans on Earth. Instead, they observe light. When a planet passes in front of its star, the star's light dims just a little. From that very small change, human beings can learn roughly how large the planet is, how long it takes to orbit its star, and whether it may be in a region that is too hot, too cold, or somewhere in between. After that, scientists continue measuring the planet's mass, size, and atmosphere. If a planet has the right size and mass, it may be able to contain more water than Earth. If light passing through its atmosphere leaves signs of certain gases, scientists can begin asking more questions. Could there be water there? Could there be an ocean? And could that environment be stable enough for life to exist? On this journey, we will mention a few names, such as K-18b TOI, 1452b, and LHS 1140b. These are not confirmed second Earths. They are simply planets that have drawn scientists' attention because the data suggests they may be connected to water in some way. Together, we will explore this question. Beyond our solar system, could there be a planet holding an ocean that human beings have never seen? Now, before we travel to those distant planets, let us begin with Earth. Not with a large telescope, not with a spacecraft, but with water. Water is everywhere around us, in a glass sitting on a table, in the moisture in the air, in rain falling onto rooftops, in rivers, lakes, oceans, and inside the human body itself. Because it is so familiar, water is often treated as something obvious. But from the perspective of the universe, liquid water on the surface of a planet is something very special. Earth is not only a ball of rock moving around the Sunday. Earth is a planet with oceans. Most of its surface is covered by water. Those oceans hold heat, create clouds, create rain, soften the climate, and give life an environment in which it can exist. Without water, Earth would be a very different place. It might be drier, hotter, colder, or simply much more silent. What matters is that water on Earth does not simply sit still in the sea. It is always moving. Water evaporates from the ocean, rises into clouds, and then falls back down as rain. Rain flows into rivers. Rivers return to the sea, and that cycle continues over a very long time. Through this cycle, water carries heat around the planet, softens the ground, nourishes plants, and helps create more stable conditions for life. When scientists search for life beyond Earth, they often begin with a simple question: is there water there? This question does not mean that water automatically creates life. A place with water does not necessarily have living organisms. But on Earth, every form of life we know needs water in some way. Because of that, water becomes the first sign worth paying attention to. We can understand it simply like this. If we want to find a garden with plants, we would care about whether that place has soil, light, and water. Having water does not guarantee that plants are there. But if there is no water at all, the chance of finding a green garden becomes much lower. It is similar with distant planets. Water is not the final answer, but it is a very important starting point. In the past, when people talked about water beyond Earth, they often thought of Mars. Mars has ancient riverbeds, traces showing that water once flowed across its surface in the past. Then scientists looked farther, toward icy moons such as Jupiter's Europa or Saturn's Enceladus. Beneath their cold ice shells, hidden oceans may exist. This shows that water does not only appear on the surface like Earth's seas. It can also hide beneath ice, deep inside a cold and dark world. From there, the question continues to grow. If there are already several places connected to water inside our solar system, then what about beyond it? Around other stars, are there planets that also hold water? Is there any world with an ocean on its surface, or an ocean deep beneath a thick atmosphere, or water locked away in ice? This is where the story becomes more difficult. With Mars or the moons of Jupiter, we can send spacecraft close enough to observe them. But with planets outside our solar system, the distance is enormous. They are so far away that even the most powerful telescopes cannot see them clearly, the way we see the moon. We cannot see ocean waves. We cannot see sandy shores. We cannot clearly see clouds drifting across their skies, the way we can in images of Earth taken from space. So, what can human beings do? Scientists begin with small signs. They measure the light of a star. They watch to see whether that light dims when a planet passes in front of it. They calculate roughly how large the planet is. They measure how heavy it may be. They look at whether it is close to or far from its parent star. From these pieces of data, they begin to estimate what the planet might be made of: rock, gas, ice, or perhaps a large amount of water. This is not random guessing. It is how science works with places too far away to touch. When we cannot reach a planet, human beings use light to understand it. Light is like a messenger. It travels through space for many years, carrying part of the information about a star, about a planet, and sometimes even about the atmosphere surrounding that planet. But we need to remember one important thing. Finding signs that may be related to water does not mean we have found an ocean. And finding a planet at a suitable distance from its star does not mean that planet is like Earth. Some planets are too hot. Some are too cold. Some have atmospheres that are too thick, pressing down on the surface with enormous pressure. There are places where water may exist, but not in a way that is familiar to us. That is why, on this journey, the word may is very important. A planet may have water. A planet may have an ocean. A planet may have suitable conditions, but science does not rush to turn possibility into fact. It needs more data, more observations, and more time. That slowness is part of what makes this story beautiful. Human beings do not stand before the universe to declare things too quickly. Human beings listen. A slight dimming of light, a tiny change in the motion of a star, a thin trace of gas in a distant atmosphere. All of these small things are pieced together, little by little, to answer a larger question. Beyond Earth, where else does water exist? When we think about that, an ordinary glass of water begins to feel different. It is not only something that quenches thirst, it is part of a larger question about life, about planets, and about Earth's place in space. On our world, water flows through rivers, falls as rain, rests in oceans, and moves through every living thing. And out there, around distant stars, there may be other worlds holding water in their own way. We do not know for certain yet, but that very uncertainty is the reason to keep observing. From here, our journey will move away from the familiar glass of water and travel a little farther. We will explore how human beings detect planets the naked eye cannot see, how the light of a star can reveal the presence of a small world passing in front of it, and why a very slight shadow in starlight can begin the story of oceans that have never been seen. After looking back at the role of water on Earth, our journey begins to move away from the familiar blue planet. In the space near Earth, water does not only exist in oceans, rain, rivers, and lakes as we usually see it. It can appear as ice, as vapor, as traces inside rock, or deep beneath the cold crust of another world. So when scientists talk about water beyond Earth, They are not only talking about blue seas like the ones on our home planet. They are talking about many different ways water can exist in the universe. Mars is often the first place people mention. Today, Mars is a cold, dry planet with a very thin atmosphere. An atmosphere is the layer of gas surrounding a planet. On Earth, this layer helps hold heat, create weather, and protect the surface from many effects of space. On Mars, however, the atmosphere is too thin for liquid water to remain on the surface for long. Even so, images sent back by orbiters and rovers show that Mars has many features resembling ancient riverbeds, dry deltas, and layers of rock and soil that were once affected by water. Those layers of rock and soil are called sediments. In simple terms, sediment is sand, mud, minerals, or tiny particles of material carried by water, wind, or ice, then deposited over time. On Earth, rivers and lakes often leave sediments at their bottoms or along their edges. When scientists see similar structures on Mars, they have reason to think that water once flowed on the red planet in the past. This does not prove that life once existed there, but it does show that Mars once had a wetter stage, very different from the world we see today. From Mars, attention continues to move toward colder places farther from the Sunday. In our solar system, giant planets like Jupiter and Saturn have many moons orbiting them. Some of those moons are covered with ice. From the outside, they look like cold, hard, silent worlds. But beneath the ice, things may be far more complex. Europa, one of Jupiter's moons, is an important example. Europa's surface is bright and covered with long cracks. These cracks suggest that its icy shell has been stretched, shifted, and changed over long periods of time. Beneath that ice, scientists think there may be a vast region of salty water. A large body of water hidden beneath ice like this is called a subsurface ocean. In simple words, it is an ocean that does not lie open beneath the sky, but is hidden under a cold outer shell. Enceladus, a small moon of Saturn, is also a special place. From the region near Enceladus's south pole, jets of material spray out into space. Inside those jets are water vapor and tiny ice particles. This has led scientists to think that liquid water may exist beneath Enceladus's frozen crust. A small, cold world very far from the sun may still hold an environment connected to water inside it. The reason places like Europa and Enceladus may be able to hold water lies in their internal heat. They are stretched by the gravity of their parent planets and nearby objects as they move. Gravity is the attractive force between objects with mass, like the way Earth pulls things toward itself. When a moon is gently stretched and squeezed again and again, its interior can warm up. This process of creating heat through stretching is called tidal heating. In simple terms, it is heat produced when a world is kneaded from within by gravity. This is important because it shows that water does not necessarily exist only in places that receive a lot of sunlight. On Earth, we are used to the sun warming the oceans, creating clouds, and maintaining the climate. But on icy worlds, heat may come from the inside. So a place that looks frozen and lifeless from the outside may still hide a deep region of water beneath its surface. From these discoveries, the idea of an ocean world becomes broader. An ocean world does not necessarily need to have surface seas like Earth. It can be a planet or a moon, where water plays an important role in its structure or environment. Water may lie on the surface, beneath ice, underground, or exist under pressure and temperature conditions, very different from what human beings are familiar with. Here, we need to keep one point clear. Having water does not mean having life. A subsurface ocean may be too dark, too cold, lacking the right source of energy, or missing the chemical ingredients needed for life to form. Water is an important condition, but it is not final proof. So when Europa or Enceladus are considered places worth studying, it does not mean scientists have confirmed living organisms there. It only means those places have one very interesting factor: the possible presence of liquid water. From our solar system, the story continues even farther. Out there are planets that do not orbit our sun, but orbit other stars. These planets are called exoplanets. They are very distant worlds, often many light years away from Earth. A light year is the distance light travels in 1 year. Light moves extremely fast, but across the distances between stars, even light needs many years to reach us. Because the distance is so enormous, searching for water on exoplanets is much harder than studying Mars or icy moons. Human beings cannot yet send spacecraft there. Telescopes also cannot clearly see their surfaces the way we can look at maps of Earth. Scientists do not see oceans, clouds, or shorelines on those planets. Instead, they must rely on the light of the star that the planet orbits. One important factor in evaluating whether water might exist is the distance between a planet and its parent star. If the planet is too close to the star, the temperature may be so high that water evaporates. If it is too far away, water is more likely to freeze. Between these two extremes, there is a region where, under the right conditions, liquid water could exist on the surface. This region is called the habitable zone. That name needs to be understood carefully. The habitable zone does not mean a place definitely has life. It also does not mean that a planet inside that zone is like Earth. It only means the planet receives enough heat for liquid water to possibly exist, if its atmosphere, pressure, and many other factors are also suitable. An atmosphere that is too thick can trap too much heat. An atmosphere that is too thin can make it hard for water to remain stable for long. So the right position is only the first step, not a conclusion. Besides location, scientists also need to know how large the planet is and how massive it is. Size tells us whether a planet is wide or small. Mass tells us how heavy it is. When these two pieces of information are combined, scientists can estimate density. Density means how tightly matter is packed inside an object. A rock and a piece of foam may have the same size, but the rock is heavier because it is denser. With planets, density can suggest whether the inside may be made of rock, metal, gas, ice, or water. Even so, density is only a clue. A planet with a lower density than pure rock may contain a lot of water, but it may also contain gas or other light materials. So scientists cannot rely on a single number to confirm an ocean. They need many kinds of data, then compare them with models. A scientific model is a way of using physics, chemistry, and mathematics to simulate what a planet may be like inside. A model is not absolute truth. It is a way to test which possibility best fits the data. Some distant planets are called ocean world candidates. A candidate means an object worth paying attention to, one that has some features matching a hypothesis, but not enough evidence for a conclusion. A planet may become a candidate if it lies at a suitable distance, has a size and mass that suggest it may contain water, or shows signs of an atmosphere worth studying. The word candidate helps keep the story accurate. It reminds us that science is still checking, not rushing to declare. Through this careful approach, water gradually becomes an astronomical question. It is no longer only something found in oceans, rain, or living bodies. It becomes a sign human beings use to read distant worlds. A layer of ice may hide an ocean. An unusual density may suggest a large amount of light material. A planet inside the habitable zone may become a target for closer observation. Each clue is small, but when placed together, they help open a wider picture. The beauty here does not lie in quickly declaring that there is a second Earth out there. What matters more is that human beings have learned how to search carefully. From cold, dry Mars to ice-covered Europa and Enceladus, and then to distant planets around other stars, water appears as a quiet clue. It does not always appear as blue seas, but wherever there is a trace of water, there is another reason to look deeper. This journey shows that the universe is not simply empty space between stars. It may contain places far colder, darker, and stranger than Earth, yet still connected to water in some way. In some places, water once flowed and disappeared. In others, water is hidden beneath ice. In others, It is only suggested through numbers about size, mass, and light. All of these still require more observation, but each clue brings the larger question a little closer. The story now begins to turn toward how human beings detect planets that are almost impossible to see directly. A distant planet may not appear as a clear point of light, but when it passes in front of its star, the starlight dims ever so slightly. That slight dimming is one of the first ways scientists can recognize that another world exists within the glow of a distant star. The hidden oceans beneath the ice of Europa and Enceladus show us something important. Water in the universe does not necessarily have to appear in the way we are used to. It can lie deep beneath the surface, hidden from view, or exist in environments very far from sunlight. From that idea, human vision begins to move beyond the solar system, toward other stars in the night sky. Every star we see is not only a point of light. Many stars may be the centers of their own systems, where planets quietly move around them. Planets that do not orbit our sun, but orbit another star, are called exoplanets. In simple terms, they are worlds belonging to other star systems, very far from Earth. In our solar system, we are used to a certain order. Earth is a rocky planet with a solid surface and oceans. Mars is also a rocky planet, but colder and drier. Farther out are the large gas planets, such as Jupiter and Saturn. A gas planet is a kind of planet made mostly of gas, without a clear solid surface like the ground beneath our feet. Because we are familiar with the solar system, human beings once easily assumed that other planetary systems would be arranged in a similar way. But when scientists began discovering planets around other stars, the picture became very different. The universe does not repeat the same pattern everywhere. There are very large planets that orbit extremely close to their stars. There are planets larger than Earth but smaller than Neptune. There are worlds that are incredibly hot, and there are also places so cold that water can exist only as ice. One kind of planet that once surprised scientists is called a hot Jupiter. First, we should understand that Jupiter is a giant gas planet in our solar system. It is very large and lies fairly far from the Sun, but in other star systems, scientists have discovered planets similar in size to Jupiter that orbit very close to their parent stars. Because they are so close to their stars, they receive intense heat, so they are called hot Jupiters. This name only refers to their large size and high temperature. It does not mean they are actually Jupiter. The existence of planets like these shows that planets can have more complicated histories than we once imagined. A planet does not necessarily stay forever in the place where it formed. As a star system develops, gravity between different objects can change their orbits. An orbit is the path a planet follows as it moves around its star. Earth follows its own orbit around the Sun, and other planets also have their own paths around their parent stars. Orbit is very important because it determines how much light a planet receives. If a planet orbits too close to its star, its surface may become so hot that water cannot remain there for long. If it is too far away, water is more likely to freeze. So when scientists study a distant planet, they always pay attention to where it is located in relation to its star. Not every exoplanet is as large as Jupiter. Many planets have sizes between Earth and Neptune. Neptune is a large planet with a thick layer of gas, located very far from the Sun. Planets smaller than Neptune, but still larger than Earth, are often called mini-Neptunes. They may have thick atmospheres, a lot of light material, and may not resemble a simple rocky planet. Another group that is often mentioned is super-Earths. The name sounds as if it means a better version of Earth, but that is not really the case. A super-Earth is simply a planet larger than Earth in size or mass, but not so large that it resembles a giant gas planet. It may be rocky, it may contain a lot of ice, it may hold water, or it may have a thick atmosphere. The name super-Earth alone does not tell us that the planet has oceans, plants, or an environment that would be easy for life. This diversity is exactly what makes the search for oceans beyond the solar system more difficult. A planet close in size to Earth does not necessarily have water. A planet larger than Earth is not automatically an ocean world. It may be dense rock, it may have a thick layer of gas, or it may contain water in a form very different from the seas on Earth. Because of this, each planet has to be studied through many different clues. The first piece of information is often size. Size tells us whether a planet is large or small compared with Earth. But size alone is not enough to understand what lies inside the planet. Two objects can be the same size, but have very different weights. A rock and a piece of foam may have the same size, but the rock is heavier because it is denser. With planets, it is the same. Scientists also need to know the planet's mass, meaning how heavy it is. When scientists know both size and mass, they can estimate density. Density means how tightly matter is packed inside an object. If a planet is large, but not as heavy as a solid ball of rock, its interior may contain more lightweight material, such as gas, ice, or water. Even so, density is only a clue. It can suggest something about the planet's interior, but it cannot prove by itself that the planet has an ocean. The atmosphere is also an important factor. An atmosphere is the layer of gas surrounding a planet. On Earth, this layer helps hold heat, create wind, form clouds, and allow liquid water to remain more stable. But on distant planets, atmospheres may be very different. If an atmosphere is too thin, it may struggle to hold heat and protect the surface. If it is too thick, it may create enormous pressure and trap too much heat, making the environment below extremely harsh. Because of this, whether a planet can have water depends on many things at once. It does not only need to be in the right location, it also needs the right size, mass, atmosphere, and temperature conditions. If just one factor is different, water may evaporate, freeze, or be held in a form very different from the oceans we know. The hardest part is that most exoplanets are too far away for us to see clearly. They do not appear as colorful spheres through a telescope. Often, scientists know they exist only because of very tiny effects on the light of their parent stars. When a planet passes in front of its star, the starlight dims very slightly. When a planet pulls on its star through gravity, the star may make a very small wobble. These signals are weak, but if measured precisely enough, they can reveal the presence of a distant world. This way of studying is different from studying the planets in our solar system. With Mars, Jupiter, or Saturn, human beings can send spacecraft close enough to take pictures and make measurements. But with planets around other stars, the data is usually more indirect. It is like being unable to walk into a house far away, but still realizing that something is inside because the light changes through the window. Despite the difficulty, discoveries over the past few decades have shown that planets are very common. Many stars do not stand alone. Around them, there may be worlds of their own, with very different sizes, temperatures, and compositions. Some are too hot to hold water. Some are too cold. Others lie in a range that makes human beings want to look more closely. Among them are planets called ocean world candidates. A candidate is an object with a few interesting signs, but not enough evidence for a conclusion. A planet may be considered a candidate if its size, mass, position around its star, or atmosphere makes the possibility of water worth studying. The word candidate helps us understand the situation correctly. Science is considering a possibility, not declaring it as fact. This is very important, because illustrations of distant planets are often beautiful. We may see a blue sphere, white clouds, gentle starlight, or even an imagined ocean surface. But most of those images are not real photographs. They are artistic illustrations based on scientific data. They help viewers imagine, but they do not replace evidence. A planet that looks like Earth in an illustration does not mean it is truly like Earth. When talking about oceans beyond the solar system, this caution becomes even more necessary. So far, human beings have not directly seen an ocean surface on a distant exoplanet. What we have are clues: size, mass, density, distance from the parent star, and sometimes a little information about the atmosphere. Each clue is like a small piece of a larger picture. They may suggest the possibility of water, but the picture is still incomplete. Even so, these small pieces are exactly what make the journey worth following. Every newly discovered planet shows that the universe is richer than older human imagination once allowed. Not every world is like Earth. Not every planet with water, if it has water, would have blue seas and clear skies. Water there may lie beneath ice, under a thick atmosphere, or be compressed under very unfamiliar conditions. What matters is not that we have already found a second Earth. What matters is that we have learned how to search more carefully. From very distant light, scientists can recognize a planet. From its size and weight, they can make careful guesses about its composition. From the gas around the planet, they can look for more clues. Step by step, strange distant worlds begin to take clearer shape in human understanding. Among countless planets, there are places too hot, places too cold, and also worlds that make human beings want to look a little longer. They do not need to be exactly like Earth to be interesting. Just a few signs that water may exist in some form are enough to make them part of a much larger search. And in that search, the distance between a planet and its star becomes very important. Not too close, where everything may be overheated, and not too far, where everything may sink into ice. Whether a planet can hold water sometimes begins with something very simple: how much warmth it receives from its star. Too much warmth, and water can easily evaporate and disappear from the surface. Too little warmth, and water can easily freeze and remain locked in the cold. Between those two extremes is a more delicate distance, where the heat is neither too intense nor too weak. If other conditions are also suitable, liquid water may be able to exist there for a long time. That special distance is called the habitable zone. The name may sound as if any planet located there could be a place where life can exist, but its meaning is much narrower than that. The habitable zone is only the region around a star where a planet may receive enough heat for liquid water to exist on its surface. If that planet also has a suitable atmosphere and pressure, it does not automatically mean there are oceans, rain, plants, or life. We can imagine the star as a distant source of fire. If a planet is too close, the heat becomes too strong. Water may evaporate, the atmosphere may change, and the surface may gradually become harsh. If the planet is too far away, the light is not strong enough to keep it warm, water is more likely to turn into ice, and the surface sinks into cold. The region between those two boundaries is where scientists begin to pay closer attention, because that is where the possibility of liquid water becomes more reasonable. But distance is only the first step. A planet in the right location may still be nothing like Earth. What happens on the surface depends greatly on the atmosphere, meaning the layer of gas surrounding the planet. On Earth, the atmosphere helps retain some heat from the sun, creates wind, clouds, and rain, and keeps temperatures from changing too extremely. Without that layer of gas, Earth's surface would have a much harder time maintaining the stability needed for liquid water and life as we know it. An atmosphere is like a thin blanket around a planet. If the blanket is too thin, warmth escapes too quickly, and the surface can become cold and dry. If the blanket is too thick, too much heat is trapped, making the planet warm up strongly. When gases in the atmosphere hold on to some heat instead of allowing all of it to escape into space, that phenomenon is called the greenhouse effect. In simple terms, the greenhouse effect is the way an atmosphere keeps warmth around a planet. The greenhouse effect is not always bad. On Earth, it is necessary. Without a natural amount of greenhouse warming, our planet would be much colder, and liquid water would have a harder time existing widely on the surface. But if this effect becomes too strong, too much heat is trapped, then a planet may become so hot that water can no longer remain as familiar oceans, lakes, or rain. Venus is a close example within our solar system. Venus is nearly the same size as Earth, but its atmosphere is extremely thick and traps heat very strongly. The surface of Venus is so hot that liquid water cannot exist there. This shows that size alone, even a size close to Earth's, is not enough to create an Earth-like environment. A planet may be at a familiar distance, with a familiar size, but if its atmosphere is different, the entire fate of its water can also be different. Mars lies on another side of the story. The red planet has a very thin atmosphere. Because the layer of gas around it is so thin, Mars has difficulty holding heat and maintaining liquid water on its surface today. Although geological traces show that water once flowed there in the past, present-day Mars is mostly a cold and dry world. From Venus to Mars, we can clearly see that position around the Sun is only one part of the picture. Atmosphere, temperature, pressure, and planetary history all help determine whether water can exist. Pressure is also an important factor. Pressure can be understood as the force of the atmosphere pressing down on the planet's surface. On Earth, suitable pressure helps water exist in liquid form under ordinary conditions. If pressure is too low, water may evaporate or freeze more easily. If pressure is too high, the surface environment can become heavy and extreme. So when we say a planet may have liquid water, we are not only talking about temperature, we are also talking about the layer of gas and how strongly that gas presses on the surface. For planets outside the solar system, identifying the habitable zone begins with the star. Not all stars are the same. Some stars are brighter and hotter than the Sunday, others are smaller, dimmer, and cooler. If a star is very bright, its habitable zone lies farther away. If a star is weaker, that zone lies closer in. Scientists have to consider how much energy a planet receives from its parent star. Energy here can be understood simply as the amount of light and heat the planet receives. A planet that receives too much energy may gradually lose its water over time. When the surface becomes too hot, water evaporates into the atmosphere. Water vapor is also a gas that can trap heat, making the planet even warmer. If this process continues, the environment may move far away from a stable state. In the opposite case, a planet that receives too little energy may become an icy world. Water may still exist, but it is locked away as ice and cannot easily take part in processes similar to Earth's oceans. This does not mean cold planets are completely uninteresting. As Europa and Enceladus have shown, water may exist beneath ice if there is a source of internal heat. But when searching for liquid water on the surface of a distant planet, the habitable zone remains an important starting point. It helps scientists narrow the search, instead of observing every planet with the same level of priority. Many exoplanets have been found around red dwarf stars. Red dwarfs are stars that are smaller, cooler, and dimmer than the Sunday. Because they give off less light, a planet must orbit closer to them to receive enough warmth. This means the habitable zone around a red dwarf lies much closer to the star than the habitable zone around the Sunday. Because of that, planets in this region may be easier to detect through certain observation methods, but their environments also need to be examined carefully. When a planet orbits very close to its parent star, it may always show the same side to that star. This phenomenon is called tidal locking. We can understand it simply through our moon. From Earth, we almost always see the same side of the moon. If a planet is tidally locked to its star, one half of the planet may always be in daylight, while the other half remains in darkness. This creates a climate very different from Earth's, where day and night alternate because the planet rotates. A tidally locked planet does not necessarily lose all possibility of having water. If it has an atmosphere thick enough, winds may carry heat from the day side to the night side. If it has an ocean, currents may also help distribute heat. But if the atmosphere is too thin or unstable, one side may become too hot, while the other becomes too cold. So the right distance must still go together with many other conditions. The activity of the parent star is also very important. Some stars, especially young or highly active red dwarfs, can release powerful bursts of radiation. Radiation is energy emitted from a source, which can include light, ultraviolet rays, or high-energy particles. A certain amount of radiation is normal because a planet needs light and heat. But if the radiation is too strong, it can affect the atmosphere and make it difficult for water to remain stable on the surface over long periods of time. Because of this, the habitable zone is more like the first circle drawn on a map, not the final stamp of confirmation. It tells us where the heat conditions are worth noticing, but it does not tell the whole truth about the planet's actual environment. A world in that zone may still be dry, frozen, too hot, or surrounded by an unsuitable atmosphere. On the other hand, some places outside this zone may still have water beneath the surface if they are warmed from within. Life on Earth depends on many factors at once. Our planet sits at a suitable distance from the Sun, has a stable enough atmosphere, has the right pressure, has broad oceans, has rock interacting with water, and has had a very long time for natural processes to unfold. If we isolate just one factor, such as distance from the Sun, we cannot understand the full reason Earth became a place where life can exist. This helps us look at distant planets more cautiously. A world in the habitable zone is worth observing, but it cannot yet be called a place with life. It is like a door slightly opened. Behind it may be a warm room, or a cold empty place, or an environment completely different from human imagination. To understand it better, scientists must continue searching for more signs from size, mass, atmosphere, and light. In the search for oceans beyond the solar system, that caution is necessary. An illustration may show a blue planet with white clouds and deep seas, but the real data is often much more modest. The data may only tell us that the planet receives a suitable amount of heat, or has an interesting size, or shows a few signs in its atmosphere. From those small pieces of information, science builds a slower and more careful picture. A planet may be at just the right distance for liquid water to be possible. But water needs more than a good location. It needs to be retained, protected, and placed in an environment that is not too extreme. If all conditions come together in the right way, water may remain long enough to become an important part of the planet. If not, it may disappear, freeze, or exist in a form that is difficult for us to recognize from far away. Seen this way, the habitable zone does not make the question simple. It only gives the question a clearer starting point. In the darkness around distant stars, scientists search for planets located where it is not too hot and not too cold. From there, they wait for more signs, little by little, to see whether water truly has a chance to exist. A world only needs to shift a little for everything to change completely. A little closer to the star, and water may struggle to remain. A little farther away, and ice may cover the surface. But somewhere between those two boundaries, a distant planet may keep enough balance for long enough to become worth noticing. From that delicate balance, the way human beings recognize a distant planet becomes something even more subtle. Not a clear photograph, not a shoreline appearing through a telescope, but only a very small change in the light of a star. A moment of dimming so slight it almost seems insignificant, yet enough to suggest that a world is passing between us and that distant light. A distant planet does not always appear in a telescope as a separate point of light. Many worlds outside our solar system are too small, too faint, and too close to the powerful light of their parent stars. If the star is like a large lamp in the night, then its planet is like a tiny grain of dust moving near that lamp. The star's light is too strong, and the planet is almost hidden inside that brightness. Because of this, scientists do not always find planets by looking directly at them. They find them by watching the light of the star. If that light changes in a regular, very small way, and repeats after a certain amount of time, the change may show that a planet is passing in front of the star. When a planet moves between us and its star, it blocks a tiny part of the star's light. From Earth, we see the star grow slightly dimmer, then return to its normal brightness. This event is called a transit. In simple terms, a transit is when a planet passes in front of its star and causes the star's light to decrease for a short period of time. We can imagine a light bulb far away. If a small object passes in front of the bulb, the light reaching our eyes becomes slightly weaker. The larger the object is, the more light it blocks. It works in a similar way with stars. When a large planet passes in front of a star, the star's light drops a little more. When a small planet passes across, the dimming is much weaker. Sometimes the decrease is so small that human eyes would never notice it, but instruments that measure light can record it. Scientists do not look only once and then make a conclusion. They monitor the star's light over a long period of time. If, after a certain interval, the light keeps dimming in the same pattern, there is a strong chance that a planet is orbiting that star. Each time the planet passes in front of the star, the light decreases. When the planet moves away, the light returns to normal. This regular repetition is one of the most important signs. To record this change, scientists create a graph of light over time. This graph shows how bright or faint the star is at each moment. When the light is stable, the line on the graph is almost flat. When a planet passes in front of the star, that line dips slightly, then returns to its original level. This dipping shape is called a light curve. In simple terms, it is the star's light drawn as a line, allowing human beings to see its very small changes. A light curve can reveal many things. The depth of the dip shows how much light the planet has blocked. If the dip is deeper, the planet may be larger compared with the star. If the dip is very small, the planet may be smaller. From this, scientists can estimate the size of the planet. They do not need to see the planet's surface, yet they can still know roughly how large it is by measuring how much starlight it blocks. The time between each dimming event is also very important. If the light drops and then repeats after only a few days, the planet may orbit its parent star very quickly and lie quite close to it. If it takes months or years for the dimming to repeat, the planet may be farther away. The amount of time a planet takes to complete one orbit around its star is called its orbital period. In simple words, it is that planet's year. Earth's orbital period around the Sun is about 1 year. Another distant planet may have a year that lasts only a few days, or much longer. Through transits, scientists can learn whether a planet exists, about how large it is, and how long it takes to orbit its star. This information is the first step in understanding whether that world may be too hot, too cold, or located at a more interesting distance. If a planet orbits very close to its parent star, its period is usually short. It receives more heat, and liquid water on the surface would have difficulty existing. If a planet orbits farther away, its period is longer, but observation also becomes harder, because scientists must wait longer to see it cross in front of the star again. The transit method has helped human beings find many planets outside the solar system. It is especially effective when a planet passes across its star from our point of view. But not every planet can be discovered this way. If the planet's orbit is tilted in a different direction, it may never pass in front of the star as seen from Earth. In that case, the starlight does not dim in the necessary way, even though the planet still exists. This is like watching a butterfly fly around a lamp. If the butterfly passes directly in front of our eyes, we see the light dim a little. But if it flies off to the side, the light does not change clearly. It is the same with distant planets. The transit method works well only when the planet and star happen to line up with our viewing direction. Another difficulty is that starlight is not always perfectly stable. Many stars have dark or bright regions on their surfaces, much like the Sun has sunspots. Sunspots are darker areas on the Sun's surface caused by magnetic activity. When these regions rotate into our view, the star's light can also change. So just because starlight dims does not mean scientists can immediately conclude that there is a planet. Scientists must distinguish between dimming caused by a planet and changes caused by the star itself. They observe many times, compare the shape of the light curve, check the timing of the repetition, and use other methods when needed. A reliable signal usually does not appear randomly once and then vanish. It has a clear repeating rhythm that matches a planet moving around its parent star. There are also cases where the light dims because another star passes in front, or because two stars are orbiting each other. Two stars orbiting a shared center are called a binary star system. If one star passes in front of the other, the total light can also decrease. This event can imitate the signal of a planet. Because of that, scientists have to check carefully to avoid confusion. A real planet usually produces a smaller dip in brightness and has features that differ from a binary star system. This carefulness makes the transit method more powerful. It is not simply seeing one dimming event and naming a new world. It is a process of repeated measurement, removing errors, checking other possibilities, and keeping the explanation that best fits the data. Every confirmed planet is the result of many quiet observations like that. What is fascinating is that from a very small shadow, human beings can open a much larger story. When starlight decreases, we know there may be a planet passing across. When that decrease is measured carefully, we learn roughly how large the planet is. When the event repeats, we learn how long it takes to orbit the star. From there, we begin to estimate whether it is close to or far from the star, whether it receives more or less heat, and whether it may be in a region worth observing more closely. However, the transit method does not tell us everything. By itself, it cannot tell us whether a planet has an ocean. It also cannot tell us whether the surface is rock, ice, or gas. It gives us only the first part of the picture. To learn more, scientists need to combine it with other data, such as mass, density, and, if possible, signs from the atmosphere. Even so, that first part is still very important. Before asking whether a planet has water, human beings need to know whether that planet truly exists. Before thinking about seas, clouds, or atmospheres, we need to recognize that this small world is moving around a star, how long its orbit takes, and how far away it may be. The transit method opens that first door. There is something very quiet about this way of discovery. A distant planet does not shine like a star. It does not call back to Earth with a clear signal. It simply passes through the light of its parent star, leaves behind a tiny dimming, and then continues along its orbit in the darkness. From very far away, human beings see that dimming and understand that a world is there. From an almost insignificant moment, the map of the universe gains a new planet. It may be a hot world, a cold world, a rocky planet, a gas planet, or a place where water may exist in some form. All of this still needs further study, but the first step has appeared in starlight. A small shadow passing across a star does not show us an ocean, but it tells us where to look next. And in the search for worlds that may hold water, sometimes a single, very slight dimming of light is enough to begin a much longer journey. Not every planet passes in front of its star from Earth's point of view. Some worlds still orbit their parent stars, still exist out there, but never block the starlight clearly enough for human beings to recognize them through a transit. If we relied only on the dimming of light, many planets would quietly be missed. So scientists also search for planets through another kind of sign. This sign is not found in the star becoming dimmer, but in the way the star moves. A planet may be much smaller than a star, but it still has gravity. Gravity is the force of attraction between objects with mass. Earth pulls human beings toward the ground. The moon pulls on Earth's oceans and creates tides, and a distant planet also gently pulls on the star it orbits. We often imagine a star standing still in the center, while a planet moves around it. That picture is simple and easy to understand, but it is not completely accurate. In reality, both the star and the planet move around a shared balance point. This point is called the center of mass. We can understand the center of mass as the balance point of the whole system, like the middle point on a seesaw. If one side is very heavy and the other is very light, the balance point will be very close to the heavier side, but it still exists. With a star and a planet, the star is much heavier, so the center of mass usually lies very close to the star, sometimes even inside it. Because of that, the star does not move in a large, easy-to-see circle. It only wobbles slightly, very gently, very slowly, almost impossible to notice with the eye. But with sensitive enough instruments, that wobble can be measured. We can imagine an adult holding the hand of a child and spinning around. The child moves in a wider circle, while the adult only leans and turns slightly around a point close to their own body. The adult is not perfectly still. A planet and a star are similar. The planet moves more obviously, while the star makes only a tiny motion because the planet is pulling on it. The star's wobble creates a sign in its light. When the star moves slightly toward us, its light changes in a very small way. When the star moves slightly away from us, its light changes in the opposite direction. This change is related to the Doppler effect. The Doppler effect is the phenomenon where waves change when the source of the waves moves toward or away from the observer. We can understand the Doppler effect through sound first. When an ambulance drives toward us, its siren sounds higher. When it moves away, the siren sounds lower. The siren itself has not changed its nature, but the motion of the vehicle changes the way sound waves reach our ears. Light is also a kind of wave. When a star moves toward us or away from us, its light changes very slightly, even though human eyes cannot see it directly. Inside the light of a star are special lines, like fingerprints of the elements in the star's atmosphere. Elements are basic types of matter, such as hydrogen, helium, carbon, or oxygen. When the star moves toward us or away from us, these lines shift a little. If they shift toward bluer light, the star is moving toward us. If they shift toward redder light, the star is moving away from us. This very small shift is called a Doppler shift. From the Doppler shift, scientists can measure the radial velocity of the star. This phrase may sound difficult, but its meaning is fairly simple. Radial velocity is the speed at which the star moves toward us or away from us along our line of sight. It does not describe the star's entire motion through space. It only describes the part of its motion that is directed toward Earth or away from Earth. If this velocity changes in a regular pattern, there may be a planet pulling the star back and forth. The method that uses this wobble to find planets is called the radial velocity method. It does not see the planet directly. It measures the way the star is gently pulled by the planet. When the measurements show that the star moves toward us and then away from us in a repeating rhythm, scientists can infer that an object is orbiting the star and causing that pull. This method is especially important because it helps us know how massive a planet is. A transit tells us the size of a planet because the planet blocks part of the starlight. Radial velocity tells us about the planet's pull on the star. The more massive the planet is, the stronger the pull, and the more clearly the star wobbles. So from the amount of wobble in the star, scientists can estimate the planet's mass. Mass means how heavy an object is, but in astronomy, it also tells us about that object's gravitational pull. A massive planet pulls on its star more strongly than a lighter planet does. If two planets have the same size but different masses, their interiors may be very different. A heavier planet may contain more rock and metal. A lighter planet may contain more gas, ice, or water. When scientists combine the size from a transit with the mass from radial velocity, they can calculate density. Density tells us whether the material inside the planet is tightly packed or lighter. A planet that is large but not extremely massive may not be a solid ball of rock. It may contain more lightweight material, such as gas, ice, or water. This is an important clue when searching for worlds that may be connected to oceans. Even so, this method also has limits. A star can wobble or change for many reasons. Its surface may be very active. It may have dark regions, bright regions, or changes in its stellar atmosphere. These changes can sometimes make the signal harder to read. Because of that, scientists must observe over long periods of time, check the repeating rhythm, and compare the results with other data to make sure the wobble is truly caused by a planet. Another difficulty comes from the direction of motion. Radial velocity only measures the part of the movement that comes toward us or moves away from us. If a star's wobble is mostly sideways compared with Earth's view, the signal will be weaker. So this method cannot find every planet. It is powerful in certain cases, but it needs to be combined with other ways of observing. Still, radial velocity has become one of the most important tools in the study of exoplanets. It helps human beings not only know that a planet exists, but also understand how massive that planet is. In the search for water, this information matters greatly. A planet having the right size is not enough. We need to know whether it is too heavy, like a dense rocky world, too light, like a gas planet, or somewhere in between, where the possibility of containing water becomes more interesting. There is a special quietness in this kind of measurement. A distant planet does not send a direct signal to Earth. It only pulls on its star with gravity. The star responds with an extremely small motion, almost like a slow rhythm in the dark. The star's light carries that rhythm through space, and many years later, human beings read it in very fine lines of light. From the outside, everything may seem still. A star remains only a small point of light in the sky. But inside that point of light, there may be a delicate dance taking place between star and planet. An unseen world gently pulls on its sun, and the light reveals that tiny pull through a very small change. When the two methods of observation are placed together, the picture of a distant planet becomes a little clearer. The dimming of starlight can reveal its size. The star's wobble can suggest its mass. From there, scientists begin to understand whether the planet is dense or light, whether it may be rock, gas, ice, or possibly contain a large amount of water. No ocean has appeared before our eyes yet, but the clues have begun to connect. A small shadow can show that a planet is passing by. A very gentle wobble can reveal how heavy that planet is. Both are silent signals, but they help human beings move closer to distant worlds. For oceans beyond the solar system, sometimes the first thing we need to hear is not the sound of waves, but the tiny wobble of a star. A distant planet can leave two very different signs in light. When it passes in front of its star, the starlight dims a little, helping human beings estimate the planet's size. When it gently pulls on the star through gravity, the star wobbles slightly, helping human beings estimate how massive that planet is. When these two clues are placed together, they begin to give us a deeper way to understand a world we cannot touch. Size tells us whether a planet is large or small. Mass tells us how heavy it is. But to understand what the inside of a planet may be made of, scientists need to connect these two pieces of information. An object can be very large, but not very heavy if it contains a lot of gas or lightweight material. Another object can be smaller but much heavier if its interior is made of dense rock or metal. This comparison of how packed something is called density. Density can be understood simply as how tightly matter is packed into a certain amount of space. A rock and a piece of foam may be nearly the same size, but the rock is heavier because the matter inside it is denser. The foam is lighter because it has many empty spaces inside. Planets work in a similar way. A world may be larger than Earth, but if its mass is not very high, it may not be made only of rock and metal. This is why density becomes an important clue in the search for planets that may contain water. Earth is a rocky planet with an interior made mostly of rock and metal. If a planet has a size close to Earth's and a density similar to Earth's, it may also be a rocky world. If its density is much lower, scientists begin to consider other possibilities. Perhaps the planet has a lot of gas, a lot of ice, or a much larger amount of water. However, density does not tell the whole truth by itself. It is like weighing a sealed box. If the box is lighter than we expected, we know it is not completely filled with heavy stone, but we still do not know whether it contains cotton, wood, water, or air. With a distant planet, the situation is similar. Density can suggest that the planet is not a solid ball of rock, but to know whether the lighter material is gas, ice, or water, scientists need much more data. A planet with low density may be a world surrounded by a thick layer of gas. That layer of gas makes the planet appear larger in observations, but it does not add as much mass as rock or metal would. A planet like this may resemble a smaller version of Neptune, with a deep and heavy atmosphere. In that case, even if the planet has an interesting size, it may not have an ocean surface that is easy for us to imagine. Another possibility is that the planet contains a lot of ice or water. Water is lighter than rock and metal, so if a world has a large amount of water, its average density may be lower than that of a purely rocky planet. But water here does not necessarily mean blue seas on the surface. It may be ice, water vapor, or layers of water compressed under extremely high pressure. On planets larger than Earth, the pressure inside may be so strong that water no longer behaves like the water in the oceans we know. Pressure is the force pressing on an object. At the bottom of Earth's deep oceans, pressure is already enormous because a huge column of water is pressing downward. On a water-rich planet heavier than Earth, the pressure in deeper layers could be far greater. Under those conditions, water may be squeezed into special forms of ice, even if the temperature is not cold, like ordinary ice. These forms of ice are not like the cold cubes in a glass of water. They are states of matter that appear under very strong pressure. This makes the idea of a planet with water more complicated. Having water does not mean having an ocean that would be easy for life. If the ocean is too deep, its bottom may be separated from the rock below by layers of high-pressure ice. On Earth, the ocean floor and the rock beneath it can exchange minerals, heat, and chemistry. Those exchanges are very important for some living environments. If water is separated from rock by a dense layer of ice, the environment may be less favorable for life as we know it. So when scientists say a planet may be a water-rich world, they are not immediately imagining coastlines, gentle waves, and white clouds. They are saying that the planet's density matches the possibility of having a large amount of water or other lightweight material in its structure. From that possibility to a true ocean, there are still many steps. Scientists need to know whether the planet has an atmosphere, how much heat it receives from its star, whether a surface exists, and where the water lies within the planet's structure. To build that picture, scientists use planetary interior models. Before holding on to that name too tightly, we can understand it simply as a way of making an inside sketch of a planet based on what can be measured from the outside. If scientists know how large the planet is, how massive it is, and how much light it receives from its parent star, they can test many different structures. A mostly rocky planet, a planet with a rocky core and a thick water layer, a planet with a large atmosphere, or a world mixed from several components. A model is not a real photograph of the inside of a planet. It is a way to test which possibility best fits the data. If a completely rocky model cannot explain the observed mass and size, scientists may try adding the possibility of gas, ice, or water. If several different models fit the data equally well, the conclusion must remain more cautious. In that case, the planet is considered worth studying further, but cannot yet be called a definite ocean world. This is especially important for planets larger than Earth but smaller than Neptune. These planets are very common among exoplanet discoveries, yet our own solar system does not have a planet exactly like them for direct comparison. Earth is a rocky planet. Neptune is a large planet with a thick gaseous layer. Worlds between these two types may be extremely diverse. Some may be rocky super-Earths. Some may be mini-Neptunes with thick atmospheres. Some may contain far more water than Earth. The absence of a nearby example makes each planet like this its own puzzle. If we only hear the name super-Earth, we might imagine a larger, bluer Earth. But in science, that name only describes size or mass. It does not guarantee oceans. It does not guarantee a solid surface. And it certainly does not guarantee life. A super-Earth may be a gentle place, but it may also be a harsh world with a heavy atmosphere and enormous pressure. Density helps narrow down these possibilities, but it does not remove all uncertainty. If a planet has high density, it may contain a lot of rock and metal. If its density is low, it may contain more lightweight material. But gas, ice, and water can all lower density in different ways. Because of this, scientists often need more information about the atmosphere to know whether the planet has a thick layer of gas. If the atmosphere is very thick, the measured size may be enlarged by that gas layer, making the planet's internal structure harder to understand. The atmosphere also directly affects whether a planet can retain water. A thin atmosphere may allow water to be lost easily. An atmosphere that is too thick may create extreme pressure and temperature. If the gas layer is just right, and the planet receives a suitable amount of heat, liquid water has a better chance of existing. But these things cannot be inferred from density alone. Density is like a door opened slightly, while atmosphere, temperature, and light from the parent star help us look deeper into the story. We can imagine the study of a distant planet as listening to a closed room from the outside. Size tells us whether the room is wide or narrow. Mass tells us whether what is inside seems heavy or light. Density gives us a sense of whether the room contains dense, heavy objects or lighter ones. But to know whether there is water, air, a surface, or only a space filled with gas, we need more signs. Planetary science is the process of combining many indirect impressions like this into the most trustworthy picture possible. For planets that may be connected to water, caution is especially important. A density number may make people think of oceans, but it is not an ocean. A model that fits a water-rich world is not proof that water lies on the surface. A blue illustration is not a real photograph. These things should be mentioned gently, because the story of ocean worlds can easily become a promise made too early. Even so, caution should not be seen as something that takes away the beauty of discovery. On the contrary, because everything is still faint and uncertain, each small clue becomes even more valuable. A distant planet cannot be placed on a scale. It cannot be drilled into for samples. It cannot be seen clearly like Earth from orbit. But through light, through the motion of its star, and through very precise measurements, human beings can still estimate how large it is, how heavy it is, and what it may be made of. When size and mass are placed side by side, the planet begins to gain more depth in scientific imagination. It is no longer only a shadow passing across a star. It becomes a world that may be dense or light, dry or rich in volatile materials, made of hard rock or filled with layers of water and ice. Volatile materials are substances that can more easily exist as gases or change state more readily than rock and metal, such as water, methane, or ammonia, under certain conditions. These substances are usually lighter than rock, so they can strongly affect a planet's density. However, a planet rich in volatile materials is not automatically a place where life would be easy. If the gas layer is too thick, the surface may be buried under enormous pressure. If the water is too deep, the environment below may be very different from Earth's oceans. If the temperature is not suitable, water may be locked in ice or turned into vapor. Each possibility opens a direction for study, but none is enough for a firm conclusion without more evidence. The important point is that human beings have learned to ask more precise questions. Not only whether a planet lies at the right distance, but how heavy it is compared with its size. Not only whether there is water, but where that water might be, in what form, and under what conditions. These questions do not make the subject more distant. They help us avoid misunderstandings and make the search more solid. A distant world may never reveal an ocean surface directly to a telescope, but if it passes in front of its parent star, we can learn its size. If it gently pulls on the star, we can measure its mass. If those two pieces of information show that the planet does not look like a simple dry rock, then the possibility of gas, ice, or water begins to enter the discussion. From there, that planet becomes a place worth observing more carefully. Light does not only tell us that a planet has passed by, it also helps human beings consider what may exist inside that planet. Not by opening it up, not by looking down at its surface, but by combining very small signs into a slow understanding. In the darkness around distant stars, each number about size, weight, and density becomes one of the first steps toward guessing whether a world may be dry and rocky, full of gas, covered in ice, or carrying more water within it than we once imagined. From those numbers, the story begins to move closer to the thin layer surrounding the planet, its atmosphere. If the star's light passes through that gas, it may carry tiny signs of the molecules present there. And sometimes, those faint signs are exactly what make a distant planet more interesting in the search for water. A distant planet is not understood only through its size, mass, or density. If that planet has a layer of gas surrounding it, the light of its star can pass through that gas during the moment when the planet crosses in front of its parent star. At that moment, the light carries very small signs of the planet's atmosphere. An atmosphere is the layer of gas surrounding a planet. On Earth, the atmosphere contains nitrogen, oxygen, water vapor, carbon dioxide, and many other gases in very different amounts. This layer of gas is not only the air living things breathe. It also holds heat, creates clouds, creates rain, protects the surface from some radiation from space, and helps liquid water remain more stable. For a distant planet, the atmosphere may also be the key to understanding its environment. But human beings cannot fly to exoplanets to collect samples of their air. The distances are too great. Even powerful telescopes often cannot see the planet as a clear sphere with clouds, oceans, or a visible surface. Because of that, scientists must rely on the light of the star. That light travels through space, reaches telescopes, and in some cases, carries traces of the gas layer around the planet. We can imagine starlight as a stream of white light passing through a very thin piece of glass. If the glass is completely clear, the light hardly changes. But if the glass has color, dust, or some substance that absorbs part of the light coming out will no longer be exactly the same as before. A planet's atmosphere can do something similar. It does not block all the light, but certain gases can absorb very small parts of it. Each kind of gas interacts with light in its own way. Water vapor absorbs certain parts of light. Carbon dioxide absorbs other parts. Methane also leaves its own trace. These traces do not appear like written words, but in scientific data, they are like tiny missing parts in the light. From those missing parts, scientists can infer which gases may be present in the atmosphere. This way of analyzing light is called spectroscopy. Before seeing it as a difficult term, we can understand it simply. Spectroscopy is the method of splitting light into many parts to see what signs are hidden inside it. A rainbow is a familiar image of light being separated into many colors. In astronomy, instruments do not only separate light into the colors our eyes can see. They also measure parts of light that human eyes cannot see, such as infrared. Infrared is a kind of light with wavelengths longer than the red light visible to human eyes. Our eyes cannot see infrared, but many molecules in an atmosphere leave clear signs in this part of light. That is why telescopes such as James Webb are so important for studying the atmospheres of distant planets. Webb observes well in the infrared, where many molecules such as water vapor, carbon dioxide, and methane can leave traces. When a planet passes in front of its star, most of the starlight still travels straight toward us, but a very small portion passes through the edge of the planet's atmosphere. This edge of the atmosphere is like a thin rim around the planet's shadow. Light passing through that rim is absorbed in a few tiny parts by the gases inside it. After that, the light continues on to the telescope. Scientists compare the light when the planet is not passing in front of the star with the light when the planet is crossing. The difference between these two measurements can contain information about the atmosphere. This method is called transmission spectroscopy. In simple terms, it is a way to read the atmosphere's composition by using starlight that passes through the gas around the planet. Transmission here means that light travels through a layer of material before reaching us. If that layer contains certain gases, those gases can remove a very small part of the light. The missing part of the light becomes a sign that helps identify them. This is one of the most delicate ways to study exoplanets. Human beings do not see clouds drifting through the planet's sky. They do not see rain. They do not see oceans. But from light passing through an extremely thin layer of gas at a very great distance, scientists can begin to suggest possibilities about the atmosphere. A planet may have water vapor. It may have carbon dioxide. It may have methane. But each possibility must be checked carefully. What we need to remember is that atmospheric signals are very weak. A planet is much smaller than its star. The gas layer around the planet is even thinner compared with the planet's size. The portion of light passing through that gas is only a tiny part of the total starlight. Because of this, the data is often difficult to read. It can be affected by noise from instruments, by the activity of the star, or by assumptions made during data processing. Noise can be understood as unwanted changes in the data. When we listen to a song but hear static in the background, that static makes it harder to hear the melody clearly. In astronomy, light data can have its own kind of static. Scientists have to separate the real signal from the noise, like trying to hear a very small sound in a room full of background noise. The parent star is also not always completely stable. Its surface can have dark regions, bright regions, or magnetic activity. These changes can affect the light received by a telescope. If they are not checked carefully, part of the signal may be misunderstood as a sign from the planet's atmosphere. Because of that, atmospheric studies require many observations, many groups checking the data, and many different ways of processing it. Even when a certain molecule is detected, the conclusion still needs caution. A molecule is a group of atoms bonded together. Water is a molecule made of hydrogen and oxygen. Carbon dioxide is a molecule made of carbon and oxygen. Methane is a molecule made of carbon and hydrogen. If scientists see the sign of a molecule in an atmosphere, it tells them that the gas may exist there. But it does not automatically mean the planet has an ocean, and it certainly does not mean there is life. For example, water vapor in an atmosphere is an important sign when searching for water. But water vapor is not the same as an ocean on the surface. A planet may have water vapor high in its atmosphere, while conditions below are too hot, too cold, or unlike Earth's surface at all. Water vapor is only one piece of information. It needs to be placed beside the planet's temperature, pressure, mass, size, and distance from its star. Carbon dioxide is similar. On Earth, carbon dioxide is a small part of the atmosphere, but it plays a role in retaining heat. On another planet, the amount of carbon dioxide may be much greater or much smaller. It may help keep the planet warm, but if there is too much of it, the environment may become harsh. One molecule can never tell the entire story of a planet. Methane is also a molecule that attracts scientific attention. On Earth, methane can be connected to biological activity, but it can also be produced by processes that do not require life, such as geological reactions. Geology refers to processes involving rocks, minerals, volcanoes, planetary cores, and changes inside a world. So if methane is found on a distant planet, it is a reason to observe further, not definite proof of living organisms. When many molecules appear together, the story becomes more interesting, but also more complex. An atmosphere with water vapor, carbon dioxide, and methane may suggest an environment worth studying. But scientists must ask how those gases could be produced, whether they can remain stable, and whether they make sense with the planet's temperature. A biological explanation is only considered seriously after non-biological explanations have been carefully examined. This caution is especially important in stories about planets that may have oceans. A sign in the atmosphere can carry the imagination very far. We may easily picture clouds, seas, rain, or even living creatures in water. But the real data is usually much smaller than that. It may only be a faint curve in a spectrum, a sign that still needs more observations to confirm. This does not make the discovery less beautiful. On the contrary, it shows the subtlety of science. From a planet so distant that it cannot be seen clearly, human beings can still learn how to read the gas layer surrounding it. Light passes through a thin region of gas, loses a few very small parts, and then continues traveling through space for many years. When that light reaches a telescope, it carries a quiet message about molecules that may be drifting in a faraway sky. We can imagine a dark room where someone has just made tea. We have not seen the cup of tea, but there is a faint scent in the air. That scent does not tell us what the whole room looks like, where the table is, or who is sitting there, but it does tell us that something interesting is present in the air. Atmospheric spectroscopy is similar. It does not show us the entire planet, but it gives us a sign to keep exploring. For planets that may be connected to water, the atmosphere is a very valuable layer of information. Without an atmosphere, liquid water on the surface is difficult to maintain for long in many cases. If the atmosphere has the right composition, it can help retain heat and provide the pressure needed. But if the atmosphere is too thick or contains too many heat-trapping gases, the environment may become extreme. So when scientists look at atmospheric signs, they are not only checking which molecules are present. They are trying to understand how the entire environment may work. A distant planet may lie in a region where it receives enough heat from its star. It may have a size and density that make the possibility of water worth noticing. But the atmosphere is where many clues become clearer. It can suggest whether the planet holds water vapor, whether it has gases related to climate, and whether its environment may be stable enough for liquid water to exist. Even so, each answer is still only part of the picture. Sometimes, atmospheric data can make a planet become famous. A signal of methane, carbon dioxide, or water vapor may make scientists want to observe it again with stronger instruments. But an early result always needs confirmation. Science does not rely on a single measurement. It needs repeating signals, comparisons between models, and careful checks to see whether another explanation may be more reasonable. A model, in this context, is a way for scientists to reconstruct what may be happening based on the data. If a spectrum shows a certain sign, they test what atmospheric compositions could create that sign. Different models can sometimes produce very similar results. When that happens, the answer cannot yet be certain. New data helps remove some possibilities and keep the ones that fit better. Because of this, reading the atmosphere of a distant planet is a slow process. It is not like opening a photograph and immediately seeing blue oceans. It is more like listening to a very faint sentence from very far away, while there is a lot of noise in between. Each observation makes the sound a little clearer. Each careful check removes a little confusion. Gradually, the picture of the atmosphere can become more trustworthy. In the search for oceans beyond the solar system, the important thing is not simply finding one beautiful molecule in the data. What matters is whether all the clues tell a reasonable story together. Does the planet receive enough heat? Is it too large and too full of gas? What does its density suggest? What signs appear in its atmosphere? These pieces of data must be placed beside one another, like small pieces of fabric stitched together into a map. That map still has many blank spaces, but those blank spaces do not make the journey meaningless. They remind us that distant oceans, if they exist, do not easily reveal themselves. They may be hidden beneath thick atmospheres, beneath ice, under enormous pressure, or simply too far away to be seen directly. Human beings can only move closer through light, through measurement, and through caution. A very thin layer of gas around a planet can remove a few small parts of the star's light. From those missing pieces of light, scientists begin to recognize water vapor, carbon dioxide, methane, or other molecules. No sound of waves appears in the data. No ocean surface emerges before our eyes. But the atmosphere, if it can be read, may tell us which places are worth listening to for longer. From that thin layer of gas, the story of distant planets begins to gain more color. It is not only about size or mass, but about traces of substances drifting in the sky of another world. And when several signs point toward the possibility of water, a planet is no longer only a shadow passing in front of a star. It becomes a place human beings want to observe again, more slowly, more carefully, in the hope of understanding whether water is truly present there. Among the distant planets found around other stars, there is one group with a name that can easily mislead us: super-Earths. That name alone is enough to carry the imagination far. We may easily think of a larger Earth, a greener Earth, with wider oceans, higher skies, and perhaps a place somewhere that is as gentle as our own home. But in science, this name does not promise that much. A super-Earth is simply a term for planets larger than Earth in size or mass, but not so large that they resemble Neptune or Jupiter. In simple terms, they are in between, larger than our world, but still smaller than the giant gas planets. The word super here does not mean better, more beautiful, or easier to live on. It only means that the planet is larger than Earth in certain measurable ways. This needs to be kept very clear. A super-Earth could be a large rocky planet, with a solid surface and stronger gravity than Earth. It could also contain a lot of ice, a lot of water, or have a very thick layer of gas around it. If that gas layer is too heavy, the surface below, if there is one, may lie under pressure so great that it no longer resembles any ground or ocean familiar to human beings. We can imagine a sealed box placed in front of us. From the outside, we only know that it is larger than the box beside it. But inside, it could contain stone, water, cotton, or only a space filled with air. Size tells us how large the box is, but it does not tell us for certain what it is holding. Distant planets are similar. A world larger than Earth can be very interesting, but its size alone is not enough to say that it has oceans. Scientists are interested in super-Earths because they appear quite often among exoplanet discoveries. The strange thing is that in our own solar system, there is no planet exactly like this. Earth is a rocky planet. Neptune is much larger and has a thick gaseous layer. Between those two types, the solar system does not give us a nearby example to compare with directly. Because of that, each super-Earth out there is like a room whose door has not yet been opened. To understand a planet like this, human beings have to begin with what can be measured. Size tells us how much larger it is than Earth. Mass tells us how heavy it is. When these two pieces of information are placed side by side, scientists can estimate density. Density is how tightly the matter inside an object is packed. A rock and a piece of foam may be the same size, but the rock is heavier because it is denser. A planet can also be dense or light in a similar way. If a super-Earth has high density, it may contain a lot of rock and metal. If its density is lower, scientists consider the possibility that it contains more lightweight material. That material may be gas, ice, or water. This is why some super-Earths make human beings think about ocean worlds. But this needs to be said slowly. Low density does not automatically mean there are seas. It only opens the possibility that the planet is not a simple dry ball of rock. A low-density planet may be surrounded by a thick layer of gas. This gas layer makes the planet appear larger in observations, but does not make it heavier in the same way rock or metal would. In that case, the planet may resemble a mini Neptune more than a large Earth. A mini Neptune means a planet smaller than Neptune, but one that may still have a thick atmosphere and an environment very different from a rocky planet. The boundary between a super-Earth and a mini Neptune is sometimes not very clear. A planet only a little larger than Earth may still be a rocky world, but if it is larger than that, it may have kept more light gases during its formation. In that case, what we see from far away may mainly be the outer gas layer, while the real surface, if one exists, is hidden deep below. The atmosphere therefore becomes a very important part of the story. An atmosphere is the layer of gas surrounding a planet. On Earth, it helps hold heat, create clouds, create rain, and protect the surface. But on a distant super-Earth, the atmosphere may be thin, thick, hot, cold, light, heavy, or completely different from what we are used to. If the atmosphere is moderate, it may help liquid water remain more stable. If it is too thick, it may trap too much heat and create enormous pressure. Pressure is the force of gas or liquid pressing on a surface. At the bottom of Earth's deep oceans, the pressure is already so great that human beings cannot go there without special equipment. On a larger planet, with a thicker atmosphere or a deeper ocean, the pressure could be far stronger. In that case, water would no longer be the soft ocean surface we imagine, but could become a heavy, dark, and difficult to predict environment. Even if a super-Earth truly has a great deal of water, it still may not resemble Earth. On our planet, the ocean has a seafloor where water touches rock and minerals. This contact is very important because it creates many chemical reactions. But on a planet with too much water, the ocean may be so deep that, in its lower layers, the water is compressed into special forms of ice by high pressure. Those ice layers may prevent the water from touching the rock underneath. This may sound strange, but it helps us understand an important point. More water is not always better. A planet covered by an extremely deep ocean may be beautiful in the imagination, but its internal environment may not be as favorable as Earth sees. Water needs to be in the right form, in the right place, under the right conditions, before it becomes part of an environment that can support life as we know it. The position of a super-Earth around its parent star is also important. If it is too close to the star, water may be heated and evaporate. If it is too far away, water is more likely to freeze. If it lies in a range where the temperature is more moderate, that planet receives more attention. The region around a star that is not too hot and not too cold is often called the habitable zone. This name only means that liquid water could exist if other conditions are also suitable. It does not mean that life is definitely there. The parent star also greatly affects the planet. A super-Earth orbiting a sun-like star receives light differently from a super-Earth orbiting a red dwarf. A red dwarf is a type of star that is smaller, cooler, and dimmer than the Sunday. Planets around red dwarfs often need to orbit closer to receive enough warmth. That close distance can expose the planet to more effects from stellar activity, such as strong bursts of radiation. Radiation is energy emitted from a source. It can be light, ultraviolet rays, or high-energy particles. A certain amount of radiation helps warm a planet, but if it is too strong, it can damage the atmosphere or make it harder for water to remain over long periods of time. So to understand a super-Earth, scientists do not only look at the planet itself, they also have to understand the star it orbits. All of this makes the name super-Earth more modest. It is not a promise of a blue world. It is only a starting point. Behind that name may be a dry, rocky planet, a small gaseous world, an icy planet, or a place with a great deal of water that still does not resemble our oceans. The universe is not required to create easy-to-understand copies of Earth. When a super-Earth is called a candidate that may be connected to water, that usually comes from several signs at once. Its size may be suitable. Its mass and density may suggest that it is not made only of rock. Its position around its parent star may allow liquid water to exist if the atmosphere is favorable enough. Sometimes, light passing through the atmosphere may also leave traces of a few interesting molecules. But the word candidate must always remain. A candidate means the place is worth observing further, not that it has been confirmed to have an ocean. A new result may make that possibility stronger. Another observation may also change the picture. Science does not treat that change as a failure. It is the way science moves closer to the truth. Illustrations of super-Earths are often very beautiful. We may see blue spheres, bands of white clouds, gentle starlight falling on an imagined surface. But most of those images are not real photographs. They are artistic interpretations of data created to help viewers imagine. The real data is usually much more modest. One dimming of starlight, one number for mass, one very small sign in a spectrum. That does not make the story less beautiful. On the contrary, it makes the search deeper. Human beings have not seen the ocean surface of a distant super-Earth. We have not seen waves. We have not seen rain. We have not seen a shoreline. But from very small signs, scientists can still distinguish whether a planet may be dry rock, rich in gas, rich in ice, or possibly capable of holding water. A super-Earth is therefore like a silent door. Behind it may be many different kinds of worlds. Some doors may open onto a hot and harsh planet. Some may lead to a world with thick gas. Some may hide more water than Earth, but that water may exist under deep, heavy, unfamiliar conditions. We cannot know from the name alone. Only data can open that door a little further. In the search for oceans beyond the solar system, super-Earths hold a special place because they stand between the familiar and the strange. Their name reminds us of Earth, but at the same time, they go beyond what Earth can represent. They may hold atmospheres more easily, may have more complex structures, and in some cases, may make the question of water more serious. What we need to keep is balance. Larger than Earth does not mean better than Earth. The possibility of holding water does not mean there is an ocean. An interesting sign does not mean life has been found. These worlds are worth noticing precisely because there is still so much we do not know, not because they have already given us the final answer. A name can carry the imagination very far, but light and data are what keep the story grounded in science. Super-Earths are not a promise of a second home. They are larger, heavier, and possibly more complex worlds than our planet. Among them, there may be places where water exists in some form. It is also possible that many of them only resemble ocean worlds in early models. Patience is necessary. A super-Earth does not need to resemble Earth in order to matter. If it helps human beings understand more about how planets form, how atmospheres are retained, and how water can exist or disappear, it has already become part of a larger journey. From these worlds, our attention begins to turn toward more specific candidates, where the numbers for size and density make the possibility of water difficult to ignore. Among the distant worlds mentioned, when we talk about planets that may contain water, TOI 1452b is a special name. It does not stand out because we have seen oceans on its surface. It is also not proof that there is already a second Earth out there. What makes TOI 1452b worth noticing lies somewhere else. Its size, mass, and density suggest that the inside of this planet may contain more lightweight material than rock, and one possibility is water. TOI 1452b is an exoplanet, meaning it does not orbit our Sun, but orbits another star. Its parent star is a red dwarf. A red dwarf is a type of star that is smaller, cooler, and dimmer than the Sunday. Because this kind of star does not give off as much light as the Sun, a planet has to orbit closer to receive a meaningful amount of heat. TOI 1452b orbits fairly close to its parent star, but because that star is dimmer than the Sun, the amount of energy the planet receives is not the same as a planet sitting too close to a bright, powerful star. The first thing that drew scientists' attention to TOI 1452b was the very slight dimming of starlight. When the planet passed in front of its star, it blocked part of the light. This event is called a transit. In simple terms, a transit is like a small object passing in front of a light bulb, making the light dim for a short moment. From the amount of light being blocked, scientists can estimate roughly how large the planet is. TOI 1452b is larger than Earth. It is not as large as Neptune, but it is not as small as our planet either. Because it lies in that middle range, it is placed in the group known as super-Earths. We need to say this clearly again. A super-Earth does not mean a better Earth. It is only a planet larger than Earth in size or mass, but not so large that it resembles the giant gas planets. The name itself does not tell us that there are oceans, clouds, or life there. To understand TOI 1452b more clearly, scientists do not only need to know how large it is, they also need to know how heavy it is. The heaviness of a planet is called its mass. Mass helps us understand how strong the planet's gravity may be, and when it is combined with size, it helps scientists estimate density. Density is how tightly matter is packed inside a planet. An object can be large but light if it contains a lot of gas or lightweight material. Another object can be smaller but heavier if it contains more rock and metal. With TOI 1452b, the data shows that the planet is several times more massive than Earth, but its density makes scientists think it may not be only a dry ball of rock. In other words, if this planet were made entirely of rock and metal, like a large rocky planet, it might have a different density. That difference opens up one possibility. Inside TOI 1452b, there may be a large amount of lighter material, such as water or a layer of volatile material. Volatile materials are substances that can change state more easily than rock and metal, such as water, methane, or ammonia under certain conditions. They are lighter than rock, so if a planet contains a large amount of these materials, its average density may be lower. This is why TOI 1452b is considered an interesting candidate in the search for worlds that may be rich in water. But the word candidate is very important. A candidate means the planet has some features that match a possibility being studied, but not enough evidence for a conclusion. TOI 1452b may be a water-rich world. It may also have a different structure, such as a rocky core surrounded by a layer of gas or lighter material. The data we have suggests possibilities, but it has not opened the entire truth inside the planet. When we hear that a planet may contain a lot of water, the imagination can easily draw a blue sphere, a world with no continents, only a deep ocean beneath the soft red light of a dwarf star. That image is beautiful, but it must stay where it belongs, as a possibility, not a real photograph. So far, human beings have not directly seen the surface of an ocean on TOI 1452b. We have not seen waves, clouds, shorelines, or the true surface of this planet. If TOI 1452b truly contains a lot of water, its ocean could also be very different from Earth's oceans. On our planet, the seas are deep, but they still make up only a very small part of Earth's total mass. Most of Earth is rock and metal. On a planet with far more water, water may not be only a thin layer on the surface. It could become a major part of the entire planet's structure. Such an ocean, if it exists, could be far deeper than Earth's oceans. The deeper you go, the greater the pressure becomes. Pressure is the force that water or gas places on an object inside it. At the bottom of Earth's deep oceans, the pressure is already strong enough to crush many devices if they are not protected. On a larger planet, with a deeper layer of water, the pressure could be many times stronger. Under extremely high pressure, water may no longer behave like the water we know. It can be compressed into special forms of ice, not because it is extremely cold, but because it is squeezed so strongly. These high-pressure forms of ice may exist at the bottom of a very deep ocean. If they form a layer separating water from the rock beneath, that ocean would be different from Earth's oceans in an important way. On Earth, seawater touches rock at the ocean floor. This contact helps create many chemical reactions, especially in places where heat from inside the planet rises upward. Some environments at the bottom of Earth's deep oceans can support life without direct sunlight. But if water on another planet is separated from rock by a layer of high-pressure ice, those chemical reactions may be limited. So a planet with more water is not necessarily easier for life. This is what makes TOI 1452b both fascinating and difficult to understand. If it is rich in water, it could help human beings understand a kind of planet for which our solar system has no clear example. If it is not an ocean world, it is still valuable because it helps scientists understand the boundary between rocky planets, water-rich planets, and planets with thick gas layers. Whatever the final answer may be, TOI 1452b belongs to the group of worlds that make humanity's map of planets richer. The parent star of TOI 1452b also matters. Because it is a red dwarf, its light is dimmer and redder than the Sun's. A planet orbiting a red dwarf can receive a moderate amount of heat even while orbiting fairly close to the star. But orbiting close to the parent star can also bring complications. The planet may be affected by stellar activity, radiation, or the possibility of tidal locking. Tidal locking is the phenomenon where one celestial body always shows the same side to the object it orbits. Our moon is a familiar example. From Earth, we almost always see the same side of the moon. If a planet is tidally locked to its parent star, one half of the planet may always face the light, while the other half remains in darkness. This does not automatically remove the possibility of water, but it makes the climate more complex. If TOI 1452b has a suitable atmosphere, winds could carry heat from the bright side to the dark side. If it has a broad ocean, currents could also help distribute heat. But if the atmosphere is too thin, too thick, or unstable, the planet's surface could become harsh. So to understand this planet, human beings need to know more about its atmosphere, not only its size and mass. An atmosphere is the layer of gas surrounding a planet. If TOI 1452b has an atmosphere, light from its parent star may pass through that gas when the planet crosses in front of the star. Some molecules in the atmosphere can absorb certain parts of the light, leaving traces in the spectrum. A spectrum is a way of separating light to see what signs of substances may be hidden inside it. Through this method, powerful telescopes can search for water vapor, carbon dioxide, methane, or other molecules. But reading the atmosphere of TOI 1452b is not simple. The signal is very weak because the planet is far away, and the gas layer, if it exists, is only a tiny part compared with the light of the star. Scientists need many observations, checks for noise, and comparisons with many models. An early sign can open a possibility, but clearer data is needed for confirmation. This is also why telescopes like James Webb are mentioned in this story. Webb can observe infrared light, a kind of light human eyes cannot see, but one that is very useful when studying planetary atmospheres. Many important molecules leave traces in the infrared. If TOI 1452b has an atmosphere suitable for observation, future measurements may help clarify whether it is a rocky planet, a planet with a thick gas layer, or a world with a great deal of water. Even so, not even Webb can turn a distant planet into a clear image like a map of Earth. It does not directly see a coastline. It does not photograph waves. It reads light. It searches for very small traces in light. The science here is like listening for a very faint sound from a distant room, not opening the door and stepping inside to see everything. TOI 1452b is therefore a good lesson in how human beings should speak about planets that may have oceans. It is interesting enough to deserve attention, but not certain enough for a conclusion. It has numbers that make the possibility of water serious, but there are still many other explanations. It allows the imagination to travel far, while also requiring caution, so that possibility does not become fact too soon. There is still a special beauty in that caution. A planet very far from us, orbiting a dim star, may be holding more water inside it than Earth does. Or it may be another kind of world that we do not yet fully understand. Whichever case is true, the light from that star system has brought human beings an important question. How many kinds of planets lie between dry rock and deep ocean? TOI 1452b does not need to be a second Earth in order to matter. It matters because it makes the question of water more specific. It is no longer only the general idea that somewhere there may be oceans. Now, human beings have a real world with real measurements, a real orbit, a real star, and real models to test. From those things, the possibility of a water-rich planet is no longer completely vague. A world this distant reminds us that oceans if they exist out there, may not resemble Earth's seas. They may be deeper, heavier, darker, and hidden beneath gas layers or enormous pressure. They may have no shore, no waves as we know them, no familiar blue color, but the possibility that water may make up a large part of the planet is already enough to make TOI 1452b a bright point in the search. The light from TOI 1452b does not tell us a complete story. It leaves only a few numbers, a few signs, a few small curves in the data. But sometimes, science begins this way. Not with a grand declaration, but with a distant planet that makes human beings pause, look more carefully, and ask whether water could exist there in a way we have never seen before. From a water-rich candidate like TOI 1452b, our attention continues toward worlds that are even more debated. There are planets that do not only suggest water through density, but also draw attention because of traces in their atmospheres. There, the question of oceans does not lie only in mass and size, but also in tiny molecules drifting through starlight. Among the planets that have made human beings think about water, K-18b is a name often mentioned with mixed feelings: curiosity, hope, and caution. It is not a small planet like Earth. It is also not a place where human beings have seen oceans, clouds, or a clear surface. But the light that passed through its atmosphere has left a few signs special enough for scientists to look more closely. K-18b is an exoplanet. It orbits a star that is smaller and cooler than the Sunday. A star like this is called a red dwarf. Because red dwarfs give off less light than the Sun, a planet has to orbit closer to receive a meaningful amount of warmth. K-18b lies at a distance that makes scientists interested, because under the right conditions, liquid water could exist there. But this is still only an early possibility, not proof that there is an ocean. K-18b is much larger and heavier than Earth. It has a mass of about 8.6 times that of Earth, and its size is also larger than our planets. A world like this cannot simply be called a second Earth. It belongs to a group often called subneptunes, meaning planets smaller than Neptune but larger than Earth. Planets like these may have thick layers of gas, may contain a lot of lightweight material, and may sometimes have structures very different from familiar rocky planets. What makes K-18b stand out is not only its size. Observations from the James Webb Space Telescope have found signs of methane and carbon dioxide in its atmosphere. Methane is a molecule made of carbon and hydrogen. Carbon dioxide is a molecule made of carbon and oxygen. On Earth, these gases play roles in the atmosphere and climate. But on a distant planet, their presence does not automatically mean there is life. They only tell us that the planet's atmosphere contains interesting ingredients. To understand why these signs matter, we need to return to how Webb reads an atmosphere. When K-18b passes in front of its star, a very small portion of the starlight travels through the layer of gas around the planet. Some molecules in that gas hold back certain parts of the light. When the light reaches the telescope, scientists split it apart and look for tiny missing pieces. This way of reading light is called spectroscopy. In simple terms, spectroscopy is like looking at the fingerprints of light to guess what kinds of gases it has passed through. Methane and carbon dioxide make K-18b especially interesting because they fit with an intriguing hypothesis, the Hycean hypothesis. The word Hycean is made from hydrogen and ocean. Hydrogen is the lightest gas, and ocean means ocean. A Hycean planet, if such a planet exists, could have a hydrogen-rich atmosphere with a broad ocean underneath. This is an important idea because it expands the way human beings think about places where water might exist. A planet does not need to be exactly like Earth to have an environment connected to water. But the Hycean hypothesis is still only a hypothesis. It is one explanation that fits some of the data, not a final conclusion. K-18b may have an ocean beneath a hydrogen atmosphere. It may also be a mini Neptune with a thick gas layer and no ocean surface that would be friendly to life. These two possibilities are very different, but from far away, they can produce some similar signs in the data. This is why K2-18b is both fascinating and difficult to understand. One point that made K2-18b widely discussed was a possible sign related to DMS. DMS stands for dimethyl sulfide, a molecule that contains sulfur, carbon, and hydrogen. On Earth, most DMS in the atmosphere comes from very small marine organisms, especially phytoplankton. Phytoplankton are tiny drifting organisms that live in water and can photosynthesize like plants. Because of this, when people hear about DMS, they may quickly think of a sign of life. But this is where we need to slow down. A signal that may be related to DMS does not mean life has been detected. Even if a molecule on Earth is often connected to living organisms, that does not guarantee it can only be made by living organisms on another planet. The environment of K2-18b is very different from Earth. Its pressure, temperature, atmosphere, light from its parent star, and planetary chemistry could all be different. So before speaking about life, scientists have to check whether that molecule could be produced without living organisms. The studies are not yet completely unified either. Some analyses suggest that the data may contain signs of DMS or related molecules. Other analyses are more cautious, saying that the evidence is not strong enough yet or could be explained in another way. This does not make the story less important. It only shows that science is working as it should. A result is checked again, compared again, and tested through different methods before becoming a trustworthy conclusion. When speaking about K2-18b, the important thing is not to turn one clue into a claim that is too large. Methane and carbon dioxide in the atmosphere are interesting signs. The Heysean hypothesis is an intriguing possibility. DMS, if it is truly confirmed, would be a signal worth studying very carefully. But none of this has proven that there is an ocean, and it certainly has not proven that there is life. Science needs more observations, more data, and more time. That caution does not make K2-18b less wondrous. On the contrary, it makes the planet feel more real. A world more than 100 light-years away, orbiting a dim star in the constellation Leo, has left a few small traces of its atmosphere and starlight. Those traces are enough for human beings to ask questions about water, hydrogen, methane, carbon dioxide, and oceans that may not resemble any ocean on Earth. If K2-18b is a Heysean world, the landscape there would be very different from home. Its atmosphere could be rich in hydrogen, lighter, and very different from Earth's air. Beneath that gas layer, if there is an ocean, that ocean could be very deep. The light from the red dwarf star could be softer and redder than sunlight. The sky, temperature, pressure, clouds, and the way heat moves around the planet could all be unfamiliar. It would not be a beach where human beings could simply step down. It would be a kind of world that science is only beginning to learn how to describe. If K2-18b is not a Heysean world, it is still important. It may help human beings understand sub-Neptunes better, a group of planets that are very common in the galaxy but have no close copy in our solar system. It may show how a planet larger than Earth holds on to an atmosphere, how atmospheric chemistry works, and why some signs can be easy to interpret in more than one way. Even without an ocean, K2-18b still teaches human beings how to read light more carefully. This is the beauty of a scientific candidate. A candidate is not an answer. It is a place where the questions become clearer. K2-18b does not give human beings a complete image, but it gives us a point of support. From that point, scientists can test atmospheric models, compare data, search for other molecules, and check which possibilities remain stronger as more observations are added. We can imagine K2-18b as a very distant house, with only faint light shining through a crack in the door. We have not stepped inside. We have not seen the room. But in that light, a few colors are missing. A few very small signs suggest that the air inside may be different from the air outside. Those signs do not tell the entire story, but they are enough for the observer to pause, take notes, and come back to look again. What is easy to forget is that all data from K-18b comes through light. No spacecraft is flying through its atmosphere. No camera has photographed its ocean surface. No water sample has been brought back to Earth. What human beings have is starlight passing through the planet's atmosphere and then reaching a telescope after a long journey. From that light, scientists try to separate extremely small signals from noise, from error, and from the activity of the parent star. Noise means factors that make data harder to read. It is like static in a very quiet piece of music. When the signal is weak, even a little noise can make the conclusion uncertain. Because of that, claims about the atmospheres of distant planets often need to be checked many times. The more unusual a signal is, the stronger the evidence must be. K-18b also reminds us that the question of life beyond Earth should not begin with imagination that moves too quickly. On Earth, life is connected to water, but a planet that may have water does not necessarily have life. A gas connected to organisms on Earth may not have the same meaning somewhere else. An ocean, if it exists, would still need energy, suitable chemistry, a stable environment, and many other conditions before it could become a place where life might exist. This does not make the question smaller, it makes the question deeper. Instead of simply asking whether K-18b has life, human beings have to ask more carefully, what is its atmosphere really made of? What is the temperature there? Does it have a surface? Where is the water, if it exists? And what processes could create the molecules we observe? These questions are less loud, but they are more solid. In the search for oceans beyond the solar system, K-18b is like a faint lamp in the distance. It does not illuminate the whole path, but it shows the direction science can continue to follow, not only measuring size, not only measuring mass, not only measuring distance from the parent star, but also reading the atmosphere, searching for molecules, testing many possibilities, and keeping caution even when the results make human beings want to hope. A planet like K-18b does not need to become a place with life in order to have value. It already has value because it makes the difficulty of the search clearer. It shows that distant oceans, if they exist, may be hidden beneath light atmospheres, beneath deep pressure, beneath signs in starlight that are difficult to read. It also shows the difference between a beautiful possibility and a scientific conclusion. So K-18b should be seen as an invitation to keep observing, not as a finished claim. It is a real planet with real data, real debates, and real limits. In the light that has passed through its atmosphere, human beings have not found the final answer, but they have found a place worth listening to more carefully. From K-18b, the image of possible water-bearing worlds becomes wider. There are not only rocky planets like Earth. There are not only icy moons like Europa. There may also be worlds that are larger, lighter in atmosphere, deeper in ocean, and far more difficult to understand. A few signs in the light are not enough to name an ocean, but they are enough to remind us that water, if it exists out there, may not take the familiar form human beings once imagined. Alongside them, LHS 1140b is also a planet far from Earth, orbiting a small star that is dimmer than the Sunday. It is not a place where human beings have seen oceans. It is also not a planet confirmed to have life. But in the search for worlds that may carry water, LHS 1140b is a name that makes scientists pause a little longer. This planet is called a super-Earth. That phrase can easily be misunderstood, so we should understand it simply. A super-Earth does not mean a better Earth, a greener Earth, or a world easier to live on. It only means that the planet is larger than Earth, but not so large that it resembles giant gas planets like Neptune. LHS 1140b is larger than Earth, heavier than Earth, and because of that, Its environment certainly cannot be imagined as a copy of our home. What makes LHS 1140b worth noticing is that it lies in the habitable zone around its star. The habitable zone is the distance where a planet receives neither too much heat nor too little, so that liquid water could exist if other conditions are also suitable. This does not mean LHS 1140b definitely has an ocean. It only means that the planet's location makes the possibility of water more worth considering. The parent star of LHS 1140b is an M-type star. In simple terms, that means it is a star smaller, cooler, and dimmer than the Sunday. Because this star is not as bright as the Sun, its habitable zone lies closer in. LHS 1140b orbits its star fairly quickly, taking only about 25 days to complete one trip around it. A year on that planet, if we use the word in a familiar way, is shorter than 1 month on Earth. But the important thing is not only where it is located. Scientists also care about its size and mass. Size tells us how large the planet is. Mass tells us how heavy it is. When these two pieces of information are combined, scientists can estimate density. Density tells us whether the inside of the planet is dense or light. If a planet is large but not as heavy as a solid ball of rock, its interior may contain more lightweight material, such as gas, ice, or water. With LHS 1140b, newer measurements have led scientists to think that it may not be a simple dry rocky planet. It may contain much more water than Earth. But water here does not necessarily mean blue seas exposed on the surface. It could exist as ice. It could be buried beneath a cold crust. It could also exist in some region on the surface if the atmosphere and temperature allow it. An easier way to imagine it is to think of an icy world. From far away, it may look like a cold sphere, with ice covering the surface. But beneath that ice, or in a region receiving enough warmth, liquid water may exist. This is what makes LHS 1140b interesting. It may not be an open ocean planet like Earth, but a colder world where water, if present, may be hidden or distributed in a very different way. One image often used to describe this possibility is a planet like a snowball, but not completely lifeless. Snowball here is not a difficult official term. It is simply an easy way to imagine a world covered in ice. If that planet has an atmosphere that holds just enough heat, there may be regions where the ice is thinner, or perhaps a patch of liquid water exposed in a place that receives more energy. But this is still only a possibility, not something that has been seen directly. An atmosphere is the layer of gas surrounding a planet. For LHS 1140b, the atmosphere is a very important point. If this planet has the right kind of gas layer, that atmosphere could help hold heat, create pressure, and make liquid water easier to maintain. If there is no atmosphere, or if the atmosphere is too thin, the surface may be too cold, and water may easily freeze. If the atmosphere is too thick, the environment may become heavy and very different from Earth. Recent observations suggest that LHS 1140b may have a heavier atmosphere, possibly rich in nitrogen. Nitrogen is the gas that makes up most of Earth's atmosphere, but this needs to be said clearly. This still needs to be firmly confirmed. Scientists cannot yet say that the atmosphere of LHS 1140b is like Earth's. They have only seen a few early signs that are interesting enough to keep observing. This is the difference between science and imagination. Imagination can immediately draw an icy world with a blue ocean exposed beneath red starlight. Science moves more slowly. It says that the current data fits several possibilities. One possibility is that LHS 1140b contains a lot of water. Another is that it has a broad layer of ice. Another is that it has an interesting atmosphere. But all of these still need more light, more measurements, and more checking. If LHS 1140b truly has water, that water may not form seas like Earth's. On Earth, oceans open beneath the sky, with clouds, rain, wind, and currents. On LHS 1140b, water may be covered by ice. It may only be exposed in one particular region. It may also lie deep beneath the surface, where light from the star does not directly reach it. So when we say this planet may be connected to water, we need to hold an image broader than a familiar ocean surface. Another reason LHS 1140b is interesting is that its parent star is relatively close on the cosmic scale. Close here does not mean human beings can travel there. It is still many dozens of light years away from us. A light year is the distance light travels in 1 year, and light moves faster than any spacecraft humans have ever built. But in astronomy, that distance is close enough for telescopes to have a better chance of studying this planet than many more distant targets. LHS 1140b also passes in front of its star as seen from Earth. This event is called a transit. In simple terms, a transit happens when a planet blocks a very small part of its parent star's light, making the starlight dim for a short time. Thanks to transits, scientists can measure the planet's size and, in some cases, search for signs of an atmosphere. When the planet passes in front of its parent star, a very small portion of the starlight can pass through the gas layer around the planet. If certain substances are present in that gas, they will absorb part of the light. Scientists read that change to find out what the atmosphere may contain. This method does not show the planet's surface clearly, but it can hint at the gas layer surrounding it. For LHS 1140b, reading the atmosphere is still difficult. The signal is very weak. The star, the measuring instruments, and the data itself can all create noise. Noise can be understood like static in a quiet piece of music. If the music is already very faint, static makes it harder to hear accurately. Because of this, a few early signs are not enough for confirmation. They only help scientists know which direction to observe next. What is notable is that current models have helped remove some possibilities. A model is a way scientists use data to test what a planet may be like. For LHS 1140b, some studies suggest that it is less likely to be a hydrogen-rich mini-Neptune. A mini-Neptune is a planet smaller than Neptune, but still surrounded by a thick layer of light gas. If LHS 1140b is not that kind of planet, then the possibility that it is a rocky or water-rich world becomes more interesting. Even so, more interesting does not mean certain. This is something we need to keep very clear. LHS 1140b may be one of the better candidates for studying the possibility of water on a distant planet, but it is still a candidate. The word candidate means a place has many signs that make it worth further observation, not that it has been confirmed to have an ocean, a pleasant climate, or living organisms. This careful way of speaking does not make LHS 1140b less fascinating. On the contrary, it makes the planet feel closer to real science. A distant world does not need to be painted as paradise in order to matter. The possibility that it may contain a great deal of water, may have an atmosphere, and may lie in a more suitable temperature range is already enough to make it an important target for observation. LHS 1140b also reminds us that a planet with water is not always a blue planet. There may be cold white worlds covered in ice that still hold water somewhere below. There may be places where only one small region has liquid water, while the rest remains frozen. There may be oceans without waves, under an open sky, lying still in darkness beneath a very thick shell of ice. Earth has made us familiar with the image of water moving across the surface. Rivers flow, rain falls, seas move, clouds drift. But beyond the solar system, water may be much more hidden. It may not reveal itself through a blue color. It may leave signs only through density, atmosphere, or a slight change in light when the planet passes in front of its star. LHS 1140b belongs to that kind of story. Quiet, but very worth listening to. If future observations confirm that this planet has an atmosphere, and if the signs of water become clearer, LHS 1140b could become one of the important worlds in the search for potentially habitable environments. But even before the final answer arrives, it already has value. It helps human beings learn how to distinguish between rocky planets, gas planets, icy worlds, and worlds that may be rich in water. The beauty here is not in a grand announcement. It is not "we have found an ocean." It is not "we have found life." The beauty lies in the fact that a distant planet around a dim star has enough clues to make human beings look more carefully. Science sometimes begins with small things like that: a light curve, a number for density, a faint sign of an atmosphere. LHS 1140b may be an icy world. It may be a water-rich world. It may have an atmosphere. It is also possible that some of today's possibilities will change when new data appears. But that uncertainty is exactly what makes it an important part of the journey. It does not give us an easy answer. It gives us a place to keep looking. In the darkness around a small star, LHS 1140b continues to complete its orbit every few weeks. From Earth, human beings receive only very small signs of that motion. But sometimes, one small sign is enough to open a larger question. Could water be existing in that distant ice, or beneath an atmosphere we do not yet fully understand, in a way we have never seen before? A planet with a lot of water often brings to mind a very beautiful image. We may easily imagine a deep blue world, where oceans cover the surface and quietly reflect the light of a distant star. But in science, more water does not always mean better. An ocean that is too deep can create conditions very different from the seas on Earth. On our planet, the oceans are vast, but water makes up only a small part of Earth's total mass. Beneath the sea is still the seafloor. Beneath the seafloor is rocky crust. Water is not separated from the solid part of the planet. It touches rock, dissolves minerals, receives heat from the interior, and takes part in many important chemical processes. The contact between water and rock is especially important. At the bottom of Earth's oceans, there are places where seawater enters cracks in the rock, becomes heated, and then flows back out carrying minerals with it. These places are called hydrothermal vents. In simple terms, they are streams of hot water on the ocean floor that carry material from inside Earth. Around these vents, some organisms can live even without direct sunlight. This shows that water does not only need to exist, it also needs to meet energy, rock, and the right chemicals. An ocean is not only a large body of water, it is part of an entire planet connected to the seafloor, the atmosphere, internal heat, and time. These connections help make an environment more active. On an exoplanet with too much water, the story may be different. If the ocean is far deeper than Earth's oceans, the pressure in the lower layers would be extremely high. Pressure is the force that water or gas places on an object. The deeper you go beneath the sea, the stronger the pressure becomes. On a world larger than Earth, with a much deeper layer of water, that pressure could go far beyond anything familiar to us. When pressure becomes too great, water can shift into very strange forms. It is no longer only liquid water like in rivers, lakes, or oceans. Under enormous pressure, water can become a special form of ice. This kind of ice does not form because of cold temperatures, but because it is compressed too strongly. It is called high-pressure ice. High-pressure ice may lie at the bottom of a very deep ocean. In that case, it acts like a separating layer. Above it is water. Below it is rock. Between them is a dense layer of ice created by pressure. If this happens, the water no longer touches the rock directly as it does in Earth's oceans. The exchange of minerals and energy may become limited. This is why a world with a great deal of water is not necessarily more favorable for life. Water is very important, but it needs to be placed in a suitable environment. If the water is too deep, too compressed, or separated from the rock below, that ocean may be less active than we might imagine. It is still an ocean, but it is not necessarily an environment like the seas on Earth. This does not mean deep ocean planets definitely cannot have life. Science should not close the door too early on possibilities we do not yet fully understand. There may be chemical pathways out there that are very different from those on Earth. But what is more certain is that we should not rush to see every water-rich planet as an easy place for life. Water is an important condition, not a guarantee. Earth is special not only because it has water. Earth is special because its water exists within a balanced system. The ocean touches rock. Rain carries minerals from land into rivers and seas. The atmosphere helps retain heat. The sun provides energy. Heat from inside the planet creates deep environments on the ocean floor. All of these things together make water a living part of the planet's system. A planet covered entirely in water but missing that exchange could be very different. It may have no continents. It may not have a seafloor in direct contact with water. It may have enormous pressure in its deep layers. It may be covered by a thick atmosphere or cold ice. From far away, it may be a very exciting candidate, but inside, its environment could be far harder to understand. So when scientists search for oceans beyond the solar system, they do not only care about whether water exists. They also need to know where the water is, how deep it is, what the atmosphere is like, what the temperature is, and whether the water touches rock. These pieces of information help distinguish a truly promising water world from a world that simply contains a great deal of water, but is too heavy, too extreme, or too isolated. A distant ocean, if it exists, may have no shoreline, no waves breaking against land, no blue surface beneath a familiar sky. It may lie beneath a thick atmosphere, under ice or under pressure, so great that water in the deep layers turns into dense ice. More water is not always better. What matters is whether that water is placed in the right kind of setting. An ocean needs not only depth, but also exchange, energy, and time. When we understand this, the image of ocean worlds beyond the solar system becomes more real. Water remains an important sign, but it needs to exist together with an environment stable enough to become a place worth hoping for. Many planets mentioned in the search for water do not orbit stars like the Sun. They orbit stars that are smaller, dimmer, and cooler. These stars are called red dwarfs. Red dwarfs are very common in the galaxy. They are smaller than the Sun, give off less light, and appear redder compared with the familiar yellow-white light of the Sun. Because they are dimmer, a planet has to orbit closer to the star in order to receive enough warmth. This means many planets that may lie in the habitable zone around red dwarfs often orbit fairly close to their parent stars. The habitable zone is the region around a star where liquid water could exist if other conditions are also suitable. Around the Sun, this region lies at the distance where Earth is. But around a red dwarf, because the star is dimmer, that zone lies much closer in. A planet around a red dwarf can orbit very close to its parent star and still not become as hot as it would if it were orbiting close to a much brighter star. At first, this may sound favorable. Red dwarfs are very numerous. If many of them have small planets, and if some of those planets lie where the temperature is suitable, the chance of finding a water-bearing world may seem larger. But the environment around red dwarfs is not that simple. When a planet orbits close to its parent star, it can be strongly affected by the star's gravity. Gravity is the attractive force between objects with mass. Earth holds the Moon through gravity. The Sun holds the planets in their orbits through gravity as well. If a planet lies very close to a red dwarf, that gravitational pull can change the planet's rotation over time. One possible result is tidal locking. Tidal locking means that a planet always turns the same side toward its star. We can understand this through the Moon. From Earth, we almost always see the same side of the Moon. If a planet is tidally locked to its parent star, one half of the planet may always face the light, while the other half always remains in darkness. A world like that would be very different from Earth. On Earth, the planet rotates, so day and night alternate. A place that is bright will later become dark. A place that is cold will later warm up. But on a tidally locked planet, the day side may always receive light from the star, while the night side may never see a sunrise. One side could be much hotter, and the other side could be much colder. This does not mean such a planet definitely cannot have water. If it has a thick enough atmosphere, winds may carry heat from the bright side to the dark side. An atmosphere is the layer of gas surrounding a planet. On Earth, the atmosphere helps share heat, create winds, form clouds, and make the climate less extreme. On a tidally locked planet, the atmosphere could act like a system for distributing warmth. If the planet has an ocean, water could also help move heat around. Ocean currents could carry warmer water from the bright side toward colder regions. Because of that, the difference between the two sides could become less extreme. A broad ocean, if it exists, would not only be a place that holds water, it could also be part of how the planet balances its temperature. But everything depends on the specific conditions. If the atmosphere is too thin, heat is difficult to transport. The day side may become too hot, and the night side too cold. If the atmosphere is too thick, the planet may trap too much heat and become harsh. If there is not enough water, or if there is no suitable surface, stability also becomes less likely. So a planet around a red dwarf must be understood through many factors at once, not only by its distance from the star. Red dwarfs also have another important feature. Some red dwarfs, especially when they are young, can be very active. They may release bursts of energy. These bursts are called flares, which can be understood simply as moments when a star sends out stronger energy than usual. Our sun also has flares, but around some red dwarfs, these outbursts can strongly affect nearby planets. If a planet lies very close to its parent star, it can receive more radiation during those flares. Radiation is energy emitted in the form of light, ultraviolet rays, or high-energy particles. A moderate amount of radiation is normal because a planet needs light and heat. But if the radiation is too strong, it can damage the atmosphere or make it harder for water to remain on the surface for a long time. An atmosphere is like a planet's protective layer. If this protection is worn away over time, water can gradually be lost to space. For some planets around red dwarfs, this must be considered carefully. A planet may lie in a location where the temperature seems suitable, but if the parent star is too active and destabilizes the atmosphere, the environment on that planet may still be extremely harsh. Even so, we should not see every red dwarf as a dangerous place. Some red dwarfs are quieter. Some planets may be better at holding on to their atmospheres. Some worlds may be massive enough to keep gas around them for a long time. It is possible that some planets have magnetic fields or other mechanisms that help protect their atmospheres. A magnetic field is a region of influence created by motion inside a planet, and it can help block some energetic particles from a star. But not every planet has a magnetic field as strong as Earth's. The important point is that red dwarfs bring both opportunity and challenge. The opportunity lies in their number. Because they are so common, there are many places to search for planets. The challenge lies in their environment. Planets around red dwarfs often need to orbit close to their parent stars, making them more likely to face issues such as tidal locking, strong radiation, and climates very different from Earth's. A sky around a red dwarf would also be unlike our own. The light may be redder, weaker, and may come from a star that appears larger in the sky if the planet orbits close to it. If the planet is tidally locked, that star may almost stand still in one place, never rising and setting like the sun does on Earth. One side of the planet would live in extended light, while the other would remain in deep night. That image is unfamiliar, but not completely hopeless. At the boundary between the bright side and the dark side, there may be a transition region where the temperature is less extreme. If the atmosphere and water distribute heat well enough, some areas could be more stable than the rest. This is only a possibility in models, not something confirmed on a specific planet. But it shows that a planet does not need to be exactly like Earth to become worth studying. When we speak about water on planets around red dwarfs, caution still needs to come first. A planet at the right distance does not guarantee an ocean. A planet with a suitable size does not guarantee a stable atmosphere. A sign of water or gas in the data is not enough to call that place a living environment. Each factor is only one small part of the picture, but that complex picture is exactly what makes the search feel more real. The universe does not simply hand human beings easy copies of Earth. It creates worlds orbiting red stars, receiving different light, facing different gravity, and living under different rhythms of day and night. If water exists there, it would also exist under circumstances very different from our own. A planet around a red dwarf may be an icy world. It may be a dry world. It may have a thick atmosphere. It may be locked with one side facing its star. It is also possible that, in a few suitable cases, liquid water still has a chance to exist somewhere on or beneath the surface. Without painting the picture too far, that possibility alone is enough to make scientists continue observing. Red dwarfs, then, are not merely the background sky for distant planets. They are part of the story. The parent star determines the amount of light, the temperature, the radiation, the orbit, and the long-term stability of the planet. To understand a world that may carry water, we cannot look at the planet alone. We need to look at the star that warms it, pulls on it, lights it, and sometimes challenges it. In the dim red light of these small stars, planets still move quietly around them. Some may be too close, too hot, too stripped away. Some may be too cold or too dark. But among those possibilities, there are still a few worlds that make human beings want to look longer. Not because they have already given us the final answer, but because they help us understand that water, if it exists out there, may have to adapt to skies very different from Earth's. Through this, we see that water does not only need a suitable location, it needs protection, stability, and time. A planet may have water, but for water to become part of a living environment, many other conditions still need to be on its side. It is at that boundary that the question of oceans gradually becomes a question about life. What makes us pause a little longer is a very small trace in the atmosphere, a certain kind of molecule that makes scientists wonder whether that environment may be more complex than a cold rock sitting in the dark. Molecules are tiny particles that make up matter. Water is a molecule. Carbon dioxide is a molecule. Methane is also a molecule. Each molecule has its own structure, and when light passes through the atmosphere of a planet, some molecules can absorb certain parts of that light. Because of this, scientists can make careful guesses about what substances may exist in that distant atmosphere. But this is also where science needs to slow down. An interesting molecule is not proof of life. A sign in an atmosphere is not a living organism. A beautiful signal in the data is not an ocean filled with fish, seaweed, or plankton. It is only a clue, and that clue needs to be placed in the right context. On Earth, some gases can be connected to life. Oxygen in Earth's atmosphere mostly comes from photosynthetic organisms. Methane can be produced by living things, but it can also come from geological processes. DMS, a molecule that has been mentioned in studies of K2-18b, is often connected on Earth to tiny marine organisms. But once we step beyond Earth, things cannot be understood too quickly through the familiar experience of our own planet. A molecule can be created through many pathways. Some are biological, meaning they are connected to living organisms. Others are non-biological, meaning they only require rock, heat, light, atmosphere, or natural chemical reactions. For example, methane on Earth can come from living organisms, but it can also form when water interacts with rock under certain conditions. So if methane is found on a distant planet, the right response is not to declare that life exists, but to keep asking where it came from. This is a very important point in the search for life beyond Earth. Scientists do not find a single molecule and then make a conclusion. They search for the full context around that molecule. Is the planet hot or cold? Is the atmosphere thick or thin? Is there water? Is there a stable source of energy? Does the parent star produce too much radiation? Do the other substances in the atmosphere make sense together? Only when many signs stand beside one another does the story become more trustworthy. A sign that may be connected to life is called a biosignature. This phrase sounds very strong, but it needs to be understood carefully. A biosignature does not mean life has been found. It only means there is a sign that could be produced by life or could be related to life, but still needs to be checked against other possible explanations. In science, the more important a sign is, the more carefully it must be tested. We can imagine seeing smoke from very far away. The smoke may come from a fire, but it could also be dust, vapor, fog, or another phenomenon we have not clearly seen. If we rush to conclude that someone is sitting beside a fire, we may be wrong. The better response is to look more closely, measure more, and check the wind, the light, the heat, and every sign around it. It is the same with distant planets. A molecule is only a thin line of smoke in the data, not the entire story. This does not make such signs less fascinating. On the contrary, it makes them more precious. At distances of dozens or hundreds of light years, simply recognizing one small component in an atmosphere is already extremely difficult. Light has to leave the star, pass through the thin gas layer around the planet, travel across a vast stretch of space, and then reach a human telescope. Within that light, the signal of a molecule may be very weak, almost buried in noise. Noise means factors that make data harder to read. It is like static in a very quiet piece of music. When the music is already soft, even a little static can make us hear it incorrectly. In astronomy, noise can come from instruments, from the activity of the star, from background light, or from the way data is processed. Because of this, atmospheric signs need to be observed many times through many methods before they become truly reliable. Life, if it exists on a distant ocean planet, may also not resemble what human beings often imagine. When people talk about life beyond Earth, the imagination easily moves straight toward large organisms, oceans filled with fish, civilizations, or images far beyond current science. But if one day human beings find signs of life on a distant world, the first kind of life scientists would most likely consider may be very small. On Earth, tiny organisms appeared very early in the history of life. Microorganisms are living things too small for the naked eye to see, but they can live in many different environments. Some live in hot water. Some live at the deep ocean floor. Some live inside rock, in ice, in very salty places, in darkness, or in places with very little nutrition. This shows that life does not necessarily have to begin with large and dramatic forms. If there is an ocean under ice, beneath a thick atmosphere, or in the darkness of a distant planet, life there, if it exists, may only be made of very small forms. It may not create any clear image. It may not change the color of the ocean. It may only leave behind a very slight change in the chemistry of the atmosphere or the water. And even that change would be very difficult for human beings to recognize from far away. That is why scientists need a combination of many signs. A planet with water is worth noticing. A planet with a suitable atmosphere is also worth noticing. A molecule that could be connected to life is even more worth observing. But each sign by itself is still not enough. They need to stand together in a more reasonable picture, where non-biological possibilities have been carefully examined. This caution can sometimes sound as if it reduces the emotion of the story, but in truth, it protects the beauty of discovery. A rushed claim can excite people for a moment, then lead to disappointment when new data does not support it. A slower conclusion built from many observations, may not be loud, but it lasts longer. In the search for life, patience is just as important as the telescope. Water is a starting point. Atmosphere is a layer of clues. Molecules are small traces in the light. But life, if it exists, needs more than that. It needs a stable enough environment. It needs a source of energy. It needs suitable chemistry. It needs time. And it needs a planet that not only has water, but also allows water to participate in a long-lasting system. When we look at distant planets in this way, the story becomes less simple but deeper. K-18b, TOI 1452b, LHS 1000, 140b, or any other candidate is not a certain promise of life. They are places that help human beings learn how to read the universe more delicately. Each small sign in the light, each molecule that may appear in an atmosphere, each possibility of water, makes the larger picture a little clearer. There is no sound of waves in the data. No living creature appears through a telescope. There is only light, very fine lines of measurement, and molecules recognized through careful work. But sometimes, that alone is enough for human beings to feel that the universe is not completely silent. It is leaving behind small traces, and we are learning how not to misunderstand them. A sign is not life yet, but it can help human beings ask more precise questions. And within that precision, hope does not disappear. It only becomes calmer, deeper, and more worthy of the vast distance between us and the oceans we have never seen. If life truly exists in some distant ocean, perhaps it would not appear in the way human beings often imagine. It would not appear as a large creature swimming through dark water. It would not change the color of a distant sea. It would not send a signal back to Earth so clear that everyone could recognize it. Life, if it ever began in a place like that, may have begun very small, very slowly, and with almost no visible trace. Earth once passed through a stage like that as well. Before there were forests, fish, birds, large animals, or human beings, this planet was home to extremely tiny forms of life. They lived in water, in mud, in rock, in places where, if we looked only with our eyes, we would see nothing but stillness. These forms of life are called microorganisms, meaning living things so small that we need a microscope to see them. Small does not mean unimportant. Over a very long time, microorganisms helped change Earth's atmosphere, influenced its oceans, affected its rocks and soil, and shaped the path that allowed more complex life to appear later. They did not create a dramatic scene like a volcano or a great storm, but their steady presence quietly rewrote the history of an entire planet. So when we think about an ocean beyond the solar system, the image closer to science is not a world filled with large creatures. A more reasonable image is a dark, deep region of water, perhaps cold or warm, depending on the place, where very small chemical reactions continue over a very long time. If life has a chance to appear, it may be only simple cells, clinging to rock, drifting in water, or existing near a source of heat in the deep. On Earth, the deep ocean floor gives us an important clue. In places where sunlight cannot reach, there are still regions where hot water and minerals flow out from inside the planet. These places are called hydrothermal vents. In simple terms, they are streams of hot water on the ocean floor, carrying material from deep inside Earth. Around them, life still exists, even without relying on sunlight the way plants do on land. This opens a gentler way of looking at life. It does not necessarily need a blue sky, a bright sea surface, or an environment that feels comfortable to human beings. In some cases, all it may need is water meeting rock, heat, and minerals, and being held stable for long enough that complex reactions can continue. Life does not always begin in the most beautiful place. Sometimes it begins somewhere very dark, very deep, and very quiet. But water alone is still not enough. An ocean can be vast and still be poor in energy. A planet can contain a lot of water, but that water may be separated from rock, buried beneath a thick layer of ice, or trapped in an environment that changes too violently. Life needs more than the presence of water. It needs a flow of energy to keep reactions going. It needs suitable material to build living structures. And it needs time for tiny processes to accumulate into something larger. Time is a very important part of this story. On Earth, water, rock, atmosphere, and life have interacted with one another for billions of years. There was no rush in that process. The great changes of a planet are often built from countless small changes repeated over long periods of time. A distant ocean, if it is to become a place worth hoping for, would also need some kind of stability. If water appears only for a short time and then disappears, the chance for life becomes far more fragile. Because of this, when scientists look at distant planets, they are not only searching for signs of water, they are also trying to understand the situation of that water. Can it remain liquid for a long time? Is it held by an atmosphere? Does it touch rock and minerals? Does the planet have a stable source of heat? Is the parent star too violent? These are not minor details. They help decide whether water is only a substance that happens to be present, or whether it is part of an environment that may support something deeper. If a very small form of life exists in an ocean out there, it may leave almost no clear sign. It may not change the atmosphere strongly enough for a telescope to recognize. It may live beneath ice, too deep for light to carry back its trace. It may exist sparsely, slowly, without creating a signal large enough for human beings on Earth to detect. That silence does not prove that nothing is there. It only shows how difficult it is to recognize life from far away. That is why the signs human beings search for are often very indirect. A little water vapor in the atmosphere, a few molecules that draw scientific attention, a density that suggests a planet may contain water or ice. Those signs do not stand alone to create a conclusion. They are like small pieces of light falling on dark water. Only when many pieces of light appear in the right places does the picture begin to become clearer. This caution does not take away the beauty of the story. On the contrary, it helps that beauty last. A rushed claim can make people excited for a moment, then fade when new data appears. But an understanding built slowly, from many observations and many careful checks, can go farther. In the search for life, patience is not the dry part of science. It is how human beings learn to respect the distance between hope and truth. There is no sound of waves in the data. No living creature appears through a telescope. There is only light passing through very distant layers of gas, measurements as thin as threads, and possibilities that must be held with care. But that silence is not empty. It is like still water at night, where we cannot yet see what lies below, but we still know that depth is there. After all of this, human beings learn a softer lesson. Sometimes the greatest things do not begin with a grand scene, but with a very small change in water, in light, or in the patience of the observer. Far from Earth, a planet may be quietly orbiting its star. If there is water there, human beings still cannot see that water's surface. No telescope today can clearly photograph a shoreline on a distant planet the way we can see images of Earth from space. Oceans beyond the solar system, if they exist, still remain beyond our direct sight. What human beings have is light. Light from the star travels through space, sometimes passing through the very thin layer of gas around a planet before reaching a telescope. During that journey, the light may change slightly. A very small part of it may be absorbed by molecules in the atmosphere. Another part continues on. When that light reaches human instruments, it does not tell a complete story, but it leaves enough signs for scientists to begin listening. The James Webb Space Telescope is very important in this journey. Webb does not see oceans on distant planets. It does not photograph waves, clouds, or the ground of worlds like K-18b, TOI 1452b, or LHS 1140b. What Webb does better is read light in the infrared. Infrared is a kind of light human eyes cannot see, but many molecules in an atmosphere leave clearer traces in this region. We can understand Webb as a pair of very sensitive ears, except instead of hearing sound, it listens to light. A distant planet does not speak. It only passes in front of its star, or lets starlight brush through its atmosphere. Webb records that very small change. From there, scientists try to find whether the gas layer around the planet may contain water vapor, methane, carbon dioxide, or other molecules. But that signal is very weak. The planet is much smaller than the star. The planet's atmosphere, if it has one, is only a thin layer compared with the planet as a whole. The portion of light that passes through that gas is only a tiny fraction of the total light coming from the star. Because of this, the data is never easy to read. It is like trying to hear a whisper from very far away, while many other sounds are interfering around it. Those interfering sounds, in science, can be called noise. Noise means factors that make data less clean and clear. It can come from the instrument. It can come from the activity of the star. It can come from the way light is affected along its path. Sometimes, a signal that first seems to belong to a planet's atmosphere becomes less certain after closer examination. Because of this, one observation is usually not enough. Scientists need to observe again. They need to see whether the signal repeats, whether it remains strong when analyzed in different ways, and whether it could be explained by the activity of the star. The more exciting a discovery is, the more carefully it must be checked. This is not useless slowness. This is how science avoids turning a faint sign into a conclusion too soon. Webb has helped human beings move farther in the study of exoplanet atmospheres. But Webb also has limits. It cannot turn every distant planet into a clear map. It cannot say with certainty where an ocean exists based on one small signal. It cannot replace repeated observations, multiple models, and different ways of checking the data. Webb's strength is that it opens another door, not that it closes every question. That makes planets that may hold water feel both closer and farther away. Closer, because human beings can now read part of the atmosphere of a few worlds very far from us. Farther, because when we read more carefully, we also realize that each signal may have more than one interpretation. One molecule may suggest water. One gas may suggest interesting chemistry. But to know whether an ocean lies beneath, the picture still needs many more pieces. Those pieces come from many kinds of observation. Size tells us how large the planet is. Mass tells us how heavy it is. Density suggests whether the interior may be rock, gas, ice, or water. The atmosphere tells us what substances may exist in the gas around the planet. No single piece is enough on its own, but when many pieces fit together, the planet begins to appear a little more clearly in human understanding. The beautiful thing here is that human beings are learning to be patient with light. A tiny point in the sky may take years to reveal only a very thin part of its story. A distant planet may need many observations before its atmosphere begins to show what it contains. A possibility of water may take a long time to grow stronger, or it may become weaker when new data appears. Science does not move forward in a straight line of certainty. It moves through small steps that are checked again and again. In the future, new telescopes may help the story become clearer. Some instruments will observe light more precisely. Some will separate the light of a planet from the light of its parent star more effectively. Some may help study smaller planets that are more similar to Earth. But even when technology becomes stronger, caution still needs to remain. Seeing farther does not mean concluding faster. Sometimes, seeing farther only helps us understand that the universe is far more subtle than we thought. Oceans beyond the solar system, if they exist, may remain hidden for a long time. They may lie beneath ice. They may lie beneath thick atmospheres. They may be too deep, too dark, or too different from Earth's oceans. But each time light passes through a distant atmosphere and leaves a trace, human beings move a little closer to understanding which places are worth observing further. There is no sound of waves in Webb's data. No blue color appears like an image of an ocean. But there are very fine lines of light, small signs of gases, changes so faint that they take years of experience to read correctly. That silence is not empty. It is the way distant worlds send back a very small part of themselves. Human beings on Earth continue listening through light, not rushing to call every sign an ocean, not turning every molecule into life, only slowly gathering each piece of data, checking each possibility, and allowing distant planets to become clearer at the pace science permits. In the vast darkness between the stars, sometimes only a small change in light is enough to keep the search going. By the end of this journey, we still do not have a real photograph of an ocean on a planet outside the solar system. No sea surface has appeared through a telescope. No wave has been seen under the light of a distant star. All human beings have are still very small signs. Starlight dimming for a brief moment, a measurement of size, a number for mass, a few traces in an atmosphere. Those signs are not enough to say that there is definitely a sea there, but they are enough to show one thing. Out there are planets worth observing further. K-18b, TOI 1452b, and LHS 1140b are not second Earths. They are also not proof of life. They are simply worlds that have drawn scientists' attention because their data is connected to water in some way. The important thing is to keep this truth very clear. Having water does not mean having life. Having water vapor in an atmosphere does not mean having an ocean. A planet located at a suitable distance from its star is not necessarily habitable. Water needs many conditions around it: a suitable temperature, a stable atmosphere, pressure that is not too extreme, a source of energy, and enough time for things not to change too quickly. So this search is not a race to declare, as early as possible, that human beings have found a world like Earth. It is more like a process of listening. Scientists listen to light, measure very small changes, check each possibility, and slowly learn more about distant planets. A correct conclusion, even if it comes slowly, is still more valuable than a grand claim without enough evidence. And when we look so far away, Earth suddenly becomes more special. Here, water does not only exist. It moves through rain, clouds, rivers, oceans, rock, soil, and living bodies. Water on Earth is not isolated. It is part of an entire system. Sunlight, atmosphere, rock, heat from inside the planet, and long stretches of time, all working together to create a stable environment. Because of that, a glass of water on a table no longer feels too ordinary. Rain outside the window is not only weather. A sea at night is not only scenery. All of them are signs of a very delicate balance that Earth has maintained for billions of years. Out there, if oceans exist, they may be very different from our seas. In some places, water may lie beneath ice. In others, it may be hidden under a thick atmosphere. Somewhere else, an ocean may be so deep that pressure makes everything unfamiliar. Those worlds do not need to resemble Earth in order to matter. They only need to show us that water in the universe can exist in many different ways. Through this story, we realize that it is not certain that life exists out there. It is also not true that human beings have found a second home. The message is simpler. Water is precious, Earth is fragile, and science is most beautiful when it knows how to hope without overstating what it has not yet proven. Perhaps one day, light from a distant planet will give us clearer evidence. Perhaps an ocean beyond the solar system will truly be confirmed. But even before that day, this journey has already changed the way we look at the sky. Each star is no longer only a point of light. It may be the place where a planet is quietly orbiting, holding ice, gas, rock, or water within itself. From oceans without names, we return to the ocean we already have. From planets we do not yet fully understand, we look at Earth more gently. And from very small signs in light, we learn something peaceful. The universe does not need to answer immediately in order to be beautiful. Sometimes, simply knowing how to search with patience is enough to bring human beings closer to both distant worlds and the planet beneath our feet.